So we're officially recording right now. Okay. So we got Dylan Shook and Vic, Patrick, McGill, Jamie. Okay, good. I'm back in the yard again, just in case if
Squirrel hunt.
You got a silhouette.
Got a silhouette. Yeah.
Wood silhouette. Yeah.
He's squirrel hunt. Times the hard, Patrick.
McGill, Dylan Shook, Patrick. 1, 2, 3, 4, 5. Okay, yeah, that's it. All right, so I made 3 videos today in the shop on labs. One of them is going to be specific for Dylan Ivy and Hunter Bruce. There was a soft starter lab that they never got to check, and I checked theirs today, ran it, and I filmed it. And so, unless they come in, I probably won't show it unless. How many of you have never seen the soft start? Didn't get a chance to do the soft start lab. None of y'all did you?
I don't remember.
We done it.
That didn't mean you do it.
I don't remember. Did we?
You did the VFD, but the VFD is actually a higher level thing than the soft starter is.
Yeah. So
you skipped over the soft starter because I didn't have but 2 of them.
Okay.
And there's a couple of people did it. And anyway, I'll put that on hold until later on. And if them guys kick in, then we'll show it then. The two that wired it. Unless you particularly, if you want to see it first, we can. But I got a feeling we better hold on. I think they may step in. Matter of fact, let me tell them that if they want to see it, they need to step in. Let's see if
I need to hurry up because we're waiting to go to the bar with Victor.
Right.
Yeah, come on.
Yeah.
Corona all over the place.
Come on. I ain't
Beer
going.
kind.
Some sweet tea. They got tea at that bar.
They got tea. Twisted tea.
I've got everybody on a list, a text list, but I can go in and unclick people. So I'm just sending this to Dylan Ivy and Hunter. And so I have figured out how to set groups up and all on this phone. This phone is okay.
Hello.
Hey, how you doing, Dylan?
Doing all right.
Yeah, we missed you today on ELC 215. We did an exam review. Are you aware of the exam going to be Tuesday?
Yes, I am. I have work today, and well, you know how that goes with heat and air. You just get calls and you have to go to them. So
Right. Okay. Tonight, before I go to bed, I'm going to upload today's video and put it in YouTube, and I'll send every one of you the link. So,
I sent you an email. So I sent you an email about the sessions I missed, so I can get like a list, so I know what I need to go back and watch before the exam, and also so I don't get zeros on anything, because I know you said you were grading those now.
Right. So, what I've got down here for you, Dylan, would be.
We want to write down so we get to my notes so I can write it all down.
You got something to write with now?
Yes, I do.
I'll read them off to you.
Okay.
Okay, it would be according to my records here, unless I'm off on it. April 7, the 9th, the 14th, 21st, 23rd, and the 28th.
Okay, it's 21st, 23rd, 28th.
and also the 7th and the 9th.
7th and 9th. Okay.
Yeah.
All right.
Now I started doing the Zoom recordings just recent, and so when you click on them, well, as of yesterday, what I'm having to do, the Zoom records okay, but the Zoom links don't work. And I talked to Marion Pope at school, and she said the other instructors had the same problem. It does a good recording, and you can save the recording to your computer. I can, but then giving you a link and people click it, and it doesn't work all the time. So she said the best thing is to put it to save it for me to save the recording to my computer and then upload it in YouTube, and that's consistent. And so that's what I did. And so tonight, before I go to bed, I'm going to put this afternoon's and tonight's recording up in YouTube, and I'll send y'all the links. So it's easy. I could even send them to you as a text that you can watch them on the phone too. It'd be easy, very easy like that to see it. So, but the previous ones, you're going to have to go in Moodle to see them because I don't have them. It takes a while to upload one on YouTube. I'll be doing good to get 2 of them in there tonight because they're a couple hours a piece. So
all right.
But the main ones I would be trying to make up because it would be the ELC 215 afternoon class. That class, we didn't have worksheets. If you remember, didn't have worksheets when this virus hit. We were doing 100% live class. So those are the main ones you need to go back and see because that's the only way I have a record of giving you a grade at all is if you've watched them videos. Because I wasn't given any worksheets at that point because we were done with them. We were done with all the labs and all the paperwork. And so you might want to focus. I mean, all of it's important, but them recordings there, that's what's going to be to keep someone from getting a 0 in a lot of days is that's the only thing that you're going to be able to get a grade from in that class is the video. So,
okay. Yeah. So I don't need a list for those because they require you to look at them before it'll check it off. And this class, you can check them off as you go. So that's how I didn't know which ones I missed. So I
didn't go in there. I haven't gone in this class yet, and they actually put that condition in there,
right?
Because I just haven't gotten around to it. And we're doing the worksheets, and it's just there's so much going on that I haven't gone in here and actually done that. And if I do it at this later date, it's not going to be accurate record keeping. You know what I mean?
Yeah.
I would have had to have started earlier in this class to be able to actually do that. So let me finish this text here. Okay, I sent Dylan and Hunter a text, and we'll see if they have time to get in. So tonight we're going to be covering VFDs, and that's chapter 36. We're backing up one from 37. And I was going to bring a VFD home. We got one back in the automation system that will accept single phase 120, and then it converts over to 3-phase 230 or 240. I could have ran that motor here at home, but guess what I found out? This motor here, the only motor I've got this a similar size for that particular drive. This motor is not inverter or not VFD rated. So all motors are not really can't handle VFD signals or waveforms because the VFD doesn't put out a clean sine wave. It puts out kind of a chopped up square wave. So you have to have a motor that's actually what they call inverter rated or VFD rated. They use the word inverter because it's just another word for a VFD. A VFD does inversion, but it does variable frequency. A plain inverter, like if you buy the plug into your cigarette lighter on your truck, it'll convert 12-volt DC over to 120 AC. And that's just strictly an inverter that inverts DC to AC. But a VFD, it does inverter function, plus it does variable frequency. So but some people still they just call it an inverter, but it's it's more than just an inverter. But motor ratings, when motors are rated as to whether they can handle a VFD or not, they rate them as to say it's either inverter rated or not. And this motor here in the back of my truck is not. So this one right here that I'm showing you, that motor is not inverter rated. Now, it doesn't tell you on the nameplate. Some motors do not tell you on the nameplate, but something told me to search. So I Googled that ball door number right there, that CWDM 3542. I Googled that, and I downloaded the data sheet for that motor. And you look in the chart on it on the first page from ball door, and it is not inverter rated. And you get in. What'll happen is if you run a motor with an inverter or a VFD that's not designed for it, inverter signals they make the windings sort of vibrate in there. They make them vibrate, and they can actually rub through and have short circuits in there. So motors that are inverter rated, they have thicker insulation. They got paper insulation in there protecting the windings. They got more insulation in them than a regular motor does, so that the vibrations that happen in the windings due to the VFD waveform, that they can handle it by putting extra insulation in. And this chapter actually shows you that. So let me pull. So what that led me to is I did 2 VFD videos today at school. I did one that was a 208 3-phase, Allen Bradley PowerFlex 4, and then I did a 480 volt PowerFlex 70. And so I'm going to be able to play them right off of this laptop, and I'll upload them tonight to the to YouTube. But I'll play them straight off of this laptop here just shortly. Okay, so let me pull up the PowerPoint, and we'll get started. Yeah, I always dread seeing a semester end because you always kind of want, a few more nights would be good to be able to cover some things. If you were at the shop, it'd be great if we had a few more nights to cover some things. But I stayed in the shop all day long. I didn't even leave for lunch to make sure I recorded certain lab stuff that I feel like you need. And so I've been there all day long. And I did the afternoon class, the automation class, I did it. Okay, so let's do a screen share. All right, ready to do screen share. And let's pull that up. There you go. And Victor, did you know about Costa?
Hey, what now, buddy?
Do you know about Costa? What's happened with him? Costantino?
No, not that important.
Huh?
About
the virus?
He's not going to work.
Uh-huh.
I don't know. I texted him earlier, but I don't want to get too
right. Yep.
Too nosy.
That's right. Yeah. Yeah. I've been texting with him. Yeah. So yeah, he's going through something right now. So everybody needs to pray for him.
Yes.
For sure. Okay. Okay. So chapter 36 on variable frequency control. And let me move these cameras over. There we go. So we're going to look at the speed of an induction motor, how it can be changed when you change frequency that you feed it with, different ways of controlling frequency. and precautions that have to be made whenever you lower frequency. And look at terms like ramping and volts per hertz. So for a 3-phase induction motor speed, it can be changed 2 ways. It can be changed by changing the number of poles, stator poles. In a motor, you have a stator windings that are stationary, and then you have you got the rotor and stator. So the stator poles, how many poles is in the stationary part of the motor with the windings? If you change that, how many poles is in there per phase coming in, then you can change the speed of the motor. Or you can just change the frequency of what's coming in. And that's what the main way things are done nowadays. Changing the stator poles, we have a drill press in the shop, and I was going to video that today, and I didn't do it. How many of you remember in our shop, you go over to the drill presses, and one of them has a knob you can turn to change the speed. Another one has two switches. And these are like heavy-duty switches, and you got to, depending on what combination you put them in, it sets the speed of the drill press. Do y'all remember seeing that drill press in our shop?
Yeah.
You do?
I seen it, yeah.
Now, that one there is doing what we're saying here at this first thing by changing the number of stator poles. If you look on the side of that motor and read what's on them 2 switches on that drill press, they're changing the number of poles they're connecting on that motor on that drill press, and you have some set speeds you can run at. You really can't vary it like in between those speeds, but you got increments of RPMs you can run on the drill press, and they're doing it by changing the number of stator poles that they're connecting. And it actually tells you that on the side of the drill press. It gives you a chart to go by of what combination of them 2 switches do you put it in for a certain RPM on the drill press. So then the other drill press has just got a very speed drive in it. It's just just a wheel you turn. This, a belt drive probably with a pulley that moves in there. But anyway, so that's 2 ways that it can be done. And I had intended on taking a picture of that, but it slipped my mind. I got tied up on the VFDs. So they mention here a side effect. If you change the frequency going to a motor, which is what we do with VFDs, it changes something called inductive reactance of the windings. And that's inductive reactance. Reactance is resistance. But it's a resistance that actually changes with frequency. So when you run a motor at 60 hertz, it has natural regular resistance in the windings, plus it develops, when it's running, it develops a reactive type resistance. At a particular frequency, it'll have so many ohms of reactance to it when it's running with power. And if you lower the frequency, that reactance actually drops. And when it does, the current increases going into the motor. So with that side effect, what they all do with VFD signals is this, is if you adjust the speed down from 60 hertz down to say 30 hertz and you cut it in half, if you cut the speed in half, they're going to cut the voltage roughly in half, because when you cut the speed down, the frequency goes down, your reactance or your inductive reactance, which is a type of resistance, it drops. The motor tries to draw more amps, the motor will overheat. So you can't bring the frequency down on a motor without also bringing the voltage down. You have to bring the voltage down at the same time in the same proportion so that you don't overheat the motor. That's kind of deep, but that's what they're saying, and it's a reality. So anytime you do change frequency, the voltage also changes. I'm going to show you recordings today I did at the shop with a scope meter that shows you the waveform. It shows the frequency in hertz and shows the voltage, and you can see how they track that way, that it changes. This chart here, can y'all see the chart?
Yeah.
That chart, it looks something kind of like something on the lines of what's on beside that drill press at the shop, where depending on what position you put those 2 switches in, it's going to change the number of poles, and it gives you a certain increment change in speed on that drill motor. So they're just showing you there that if, depending on how many poles you have in a motor per phase and what frequency you have going into it, that's how it's figured what speed the motor's actually going to run at. So now this is a more primitive way of changing speed on a motor, on an AC motor, is they're showing here of using an alternator and having a DC motor and power supply, and they're varying that signal going to an alternator, and then the alternator is actually producing AC for them induction motors. That's primitive. Nobody's doing that now. It's, you know, that I would know of. It's like everybody's using VFDs. So this is a particular VFD, and if you notice, it says inverter. It's a Vectru inverter made by WEG. WEG is just another company that makes them. You know, they're not as popular as Allen Bradley, but that's a picture that they have in the book. You got your programming pad there. Now, inside of your VFDs, what they do basically is this in a nutshell. All VFDs that I know of, they work on this one principle. They'll take the incoming power, if it's three-phase, they will convert it to DC. Now, if you focus on this schematic here, this is the internal parts of a VFD in general. It's kind of generic. The L1, 2, and 3 on the left side, it comes into the VFD. It goes through this circuitry. And then when it goes through that inductor, that coil, and that capacitor, these are actually diodes or SCRs. These are SCRs, they're like diodes, but they have gate control on them. The three-phase power that comes in is converted into DC at this point right here. When it leaves these SCRs, goes through that inductor and that capacitor, then it's no longer AC anymore. The AC is actually gone. So it takes a three-phase power, it converts it to a high voltage DC at that point you see where I'm pointing at? Mm-hmm. Yeah. At that point, inside the VFD, at that point, the three-phase power is gone. It's gone. It's converted to nothing but straight line DC with no waves in it. So then at that point, and there's more circuitry to it than this, at that point when it's DC, then the VFD, it looks at the speed request that you gave it through the speed pot or through your keypad or from a PLC. It looks at what speed did you request. Did you request 60 hertz or 50 or something else or 40? And at that point, then it takes that DC and it runs it through these transistors here that are fast switching transistors, and it converts that DC back into an artificial AC for that motor out there at the exact frequency that you've asked for. So it goes from AC out here to DC here, and from DC here back to AC at a new frequency. Does that make sense?
Yeah.
Okay, so that's the way they do it. When I'll show you with a scope on a video I'm going to play in a few minutes how that the incoming voltage, of course, doesn't change. It's rock solid 60 hertz. But what leaves the drive is not even a clean sine wave. It's a choppy looking square wave. It looks kind of jagged looking, but it does vary in frequency, and that's what they generate for these motors. And again, all motors really can't handle that type of a waveform. They have to be inverter rated. But that's the generic circuitry that would be inside of all your VFDs, something along them lines. Now, this is the square wave that's actually a clean square wave. The ones out of the drives are actually a little more ragged looking than that. You'll see it in a minute. But that's what the drive produces. It's not a clean sine wave. Again, it takes a special motor to be able to handle it. And then you can also see them coming out of the VFDs that look like that. It can have a stepped wave, but in all cases, it's gonna look sharp, and it's gonna look kind of a square or rectangle looking. It's gonna be a stepped wave or square wave when you look at the outputs that are going to the motors. They mention a problem of harmonics. Now, in that waveform right there, within that waveform, you have harmonics. And harmonics, without trying to get too deep, a harmonic would be a multiple of your main frequency. So all square waves or stepped waves contain harmonics of the main frequency. So if you have a square wave that's at 60 hertz, then within that square wave, contained in it, you can have multiples of 60. So the first harmonic would be double that. It would be 120 hertz. And then if you do it again, and it keeps multiplying the multiples of the 60 hertz. It is complex. What we're getting at here is, but harmonics are contained in VFD outputs, okay? And they can have an adverse effect on the windings in a motor. So the windings have to be extra beefed up as far as the insulation around. They actually put thick paper or cardboard or paper around them so that the vibrations from the harmonics in there that actually causes vibrations in the windings. So it actually cause them to cut through and short out inside the motor. And they use bipolar transistors. That's you're getting deep in electronics, which is what I studied back in the 80s, is electronics. So here they're showing the newer circuitry inside the VFDs. Your three-phase would come into the left. It would go through these diodes, go through an inductor and a capacitor. At that point, it's pure DC, very extremely high voltage, like way up in the hundreds of volts. And then at that point, this circuitry is actually monitoring your speed request, and it actually takes that DC and produces that chopped up looking square wave out to the motor. So that's a very simplified version of it, but that's, it goes AC to DC back to AC at some new frequency. Now this is really what it looks like leaving the drive going to the motor. It looks very choppy looking like that. And what goes on here is you see those lines, there's a line and then nothing, and there's gaps between there. That's actually what those transistors are doing. What they're doing is out there, the red ones out there, they're called insulated gate bipolar transistors. They are extremely fast switching transistors. And all of those little spikes that you see out there on that wave that you just saw are produced by those IGBT transistors there, and they produce this. Okay, so it looks like a series of spikes, at positive and in negative, but the motor will actually run on that. If it's insulated well enough, a motor will run on that, and that's what your VFD signals look like to a large extent. And you'll see it in a second with the scope. And they call it pulse width modulation. It's accomplished by turning the voltage on and off several times during each half cycle. That's kind of deep, but that's really what the VFDs are producing. Now, here, this is actually a little more accurate. It shows you that the VFD produces like a narrow spike or pulse, a little bit wider, and it gets wider in here. So the on time, the on duration of each pulse in here gets a little bit longer each time in the purple. So what you end up with is this. The effective energy that the motor receives, it looks kind of like, it actually ends up being like the effective energy of a sine wave, because here, as it rises, as a sine wave would rise, they do a wider pulse width modulation in here. So your effective energy is kind of like a sine wave. The motor runs on it. The motor runs on it. Your plants are full of the motors that are running off of a signal that looks like that. And again, they mentioned the problem of harmonics that are contained in the waveform that goes to the motor. Those spikes can actually damage a motor if it's not insulated well enough, if it's not specially made. Again, this, if you take a look right here, they show you that they're putting insulation paper around the windings. You see that in the blue or the green? So that's what they do. They actually have to beef up the internal winding insulation in the motors to make it inverter or VFD rated. And they also may put a separate blower in there for continuous cooling. But insulating paper between windings and the stator core is common. And they'll actually add phase paper or insulation to the terminals in the cat head if you got terminals there. And then the wire inside the motor, which is magnet wire, it says it has a higher rated insulation around the windings in there. They have a higher rating on the insulation, and then the case sizes of these motors are typically bigger. This is a motor I just Googled last night, and I want you to look at where I'm going to point right there. It's going to tell you, you see where it says it's designed for inverter right here? Can y'all read that?
Yes, sir.
So this motor, this is a ball door motor, and it's designed for inverter or vector applications. So the motor I have in the back of my truck that I was going to hook to a VFD out here tonight, it didn't say it didn't say anything on the nameplate about it. So I Googled it, and it said it's not. It is not inverter rated. As a matter of fact, if I can, I think I saved that motor data. I didn't save it, and I'm not going to waste your time.
The only way to know for sure, the only way to know for sure, like, see, we got a rack full of motors.
Right.
You would literally have to take the nameplate and look it up to make sure that it had that.
You absolutely would. Look, I'm going to punch in. I think I can get it real quick here. I'm going to punch this up, and I'm going to show you my webcam about this motor here that it says it is not inverter rated. So I didn't want to damage a good motor. So here I am. I had to record today what I wanted to show you live out here tonight. I had to record it because I don't have anything close to a 1-horse motor that would work with that VFD that's a single phase input. So it messed up my plans because I but I did check, and I'm not going to damage that motor. So let's see. This is a ball door. You can, if you want to try this while I'm doing it, you can. It's a ball door. BALDOR CWDM 3542. And I scrolled down to where it says ball door catalog, and that's going to give you a table with everything about that motor. That's what I looked up last night. Okay. Okay, so down in there, let's see. Right, here we go. This is the data sheet. I'm going to flip over so I can see large screen here. I'm going to cut screen share off just briefly here. Okay, so this is the motor here that is showing. And let me go down to where it says that it's not inverter rated. You scroll down to where it says specs, and I'm going to hit specs in here. And it's got a lot of information in here. Let me find where it says inverter rated at. Now, look right here. It says inverter code, and it says not inverter. You see that?
Yeah.
Hold on.
Yep.
So this motor, my plan was to use this motor right here, but I can't, because what's going to happen is the windings in there could actually, from the spikes coming from that drive, it could actually end up causing, well, the magnetic field from the waveform of a VFD causes magnetic pull and movement of those windings. It causes a movement in there, and they have to be extra insulated, or it will actually damage and ruin the motor. And that could be very hazardous, extremely hazardous, if someone's standing near and that happening. it can be very hazardous. So what I don't understand is why don't they go ahead and actually put it on the nameplate? But some do and some don't. So that's just a warning there that you have to go by. And when you go to order motors, of course, make sure you're actually better off trying to stick with inverter rated motors, because a lot of things are going that way if they have it already. You can make your machines run better if you do use drives on them, VFDs. So you have a lot more control. Now let's go back to screen share. And let's see. Got Jameson. Put you in there. All right. Okay, so let me hit the screen share again. So that was just an example there. And then you go on, let's see, where are we at? Now, VFDs that are going to run motors that are over 500 horsepower, they're using SCRs, which is a silicon controlled rectifier, and GTOs, gate turn-off devices. And the schematic, this is a general schematic of what can be going on inside the inverter. Not that you're concerned with that, but they're just showing you. They're taking the DC power that's in the inverter that is taking the AC and then converted it into DC. And then in this point, they're actually converting the DC back to AC out here for the load. So they're showing you two pictures here, and I'm not going to dwell on this, but right over here, in this case, they're turning on both of the A SCRs they're turning on, that purple one and that purple one there. When they turn those on, the current flows, the DC current flows up this way through that one, and it flows through the load to the left because the purple ones are on and the black ones are off. Now, then they flip it and they turn the B's on, both of the B SCRs turn on, and when they do, the current then flows from the bottom up to here to the right through the load. And so they switch the SCRs very rapidly, and it causes the DC to produce a stepped square wave that goes to the load. It's not smooth. It's jagged, ragged looking, but that load actually sees AC. It doesn't see DC, but again, that's kind of what they're doing. And features of your VFDs are, or some of the parameters are, speed control, current limit, speed regulation, ramping, which would be accelerating, deceleration, a parameter called volts per hertz. And that parameter there, what that means is volts per hertz, if you get it specifically in our book, and it's actually a parameter on some drives you can go in there and change. Let me give you their exact wording of it. On page 350, it says that parameter called volts per hertz, it sets the ratio by which the voltage increases as frequency increases or decreases as frequency decreases. So it's a ratio. So if you change from 60 hertz down to 50 hertz, that ratio of 50 divided by 60, that ratio, you can say, well, in what ratio is the voltage going to decrease? So that parameter there would actually set how much is the drive actually going to decrease the voltage compared to the change in speed. And that's it, because they're going to bring voltage down. It's going to bring voltage down if you bring frequency down. And then you can also adjust, you can set limits on the maximum hertz and the minimum hertz on these drives. For instance, the parameters, these are the parameters on the basic PowerFlex 4 drive that we have in our shop that some of you did wire. I know Jamie and Patrick wired and programmed it, and Victor and McGill did, and well, quite a few people did, but maybe half the class. maybe the half the class actually got a chance to actually program this. But if you see in here, the parameters, basic parameters are consistent of nameplate volts, nameplate hertz, overload current. Here goes your minimum frequency and your max. So if you don't want the VFD to ever go above 50 hertz, you can go in there and put that as a max. And even if they turn the speed pot wide open, the maximum on the speed pot will be 50 hertz. Or if they're doing it through a keypad, it won't go above 50. The operator's not going to be able to get it to go above 50 if that's what you set the limit for. And then there's other parameters we're going to go over in a minute with the video where I'm showing you how to program the ones at school and showing you them running. Okay. That's showing a large VFD that can run 450 horse up to 2,500 horse motors and 380 volt to 690. So,
that's a house right there.
Yeah, house. Yeah. I got a cousin that's been involved in some real big stuff like that with Precious, and they're into some heavy duty stuff. And this is just showing here how if you have a pickup coil or a Hall effect sensor on the motor, then the VFD can actually monitor that speed and regulate speed. It can actually adjust if it can monitor, and that's just one way it could be done for speed regulation. That connection would not be on the front. It would actually be on the rear, more than likely like a tachometer or an encoder on the back of the motor.
This thing had to have one heck of a bearing on it.
Yeah. Well, what you have there is everything I've ever seen that was for monitoring speed on a motor was always mounted on the back, and it would be a little small encoder or tachometer with a small shaft, and the small shaft on that encoder would be coupled onto the rear shaft of the motor by way of a flexible coupling. So like a spring type coupling would join the motor shaft to the encoder or tachometer, and as the motor turns, it would turn that spring-like coupling, which would actually drive the encoder or tachometer. And so there was some flexibility in there, and it would drive, and then the wiring for your tachometer or encoder on the back, it would go back to a cable back to your VFD and or servo motor or servo drive, and then that was the way you could actually regulate speed real accurately. Those are internal circuit boards in some of the drives. This is a newer. That's PowerFlex 40. We got 4 and 70 at our shop. Now, so next, let me show you a live video here that I did today at school. And let's go down here. And let's go right there. And let's see, 430. That's the PowerFlex 70. That was not that. Go back. Let's go back. 430. That's a soft starter. Let me try one more here. There we go. Now, Victor, this is your drive right here, man. Victor still with us? This is one that Victor and McGill wired up, and they did get to see it run, but we're going to go through some stuff now that I just showed today. So did you hear any audio there?
No.
Okay, now let me back up and turn. There's a feature that I can turn audio on for this. Let's go back here. Hit stop share. There's a menu at the bottom that I can do. Let's see if I can find it.
Strong enough for that?
Huh?
So your internet gonna be strong enough to show that video?
We're gonna try it. There wasn't time to upload it in YouTube today. I barely had time to record them. And see, I had to teach the afternoon a live class. And let me see if I can. There's a feature down here to share computer audio. Okay, audio. I'll go back up to here. Test speaker. Share screen, recording. Just give me a minute to find it. I found there was a feature that you can, because I did it the other night with y'all. Let's go down. Advanced. It's not in there. Let's see, where is it at? Give me a second to find it. So for audio, no, it's not in there. Share screen, advanced sharing options. No, that's not it. That's not it. I'll just simply talk to you while it's playing. I know there's a way to make the audio show. It was an audio feature, audio settings. Mute my mic. Separate audio. Automatically join audio by computer when joining a meeting. No, that's not it. Video. Okay, I'm not seeing it. So I think I'm just going to talk while the video is going. That's not a problem, and it may actually be better. I'll do that. I'll go ahead and show it, and I'll just talk. Unless there's, no, that's not it. Instead of wasting your time, I'm going to go ahead and just show it. So, and I can talk fine while it goes on. So, where was it at? It was a, there. I thought I already had it opened up. Let's go back. Go back to screen share. Hey, right here it is, guys. Look, when I hit screen share computer sound, I found it. Thank the Lord. That's good. I knew I had stumbled across it, kind of. You know how I'm saying? I stumble. So I stumble into a lot of stuff. All right. So I'm doing screen share there, and let's go to, where was the video? Because I had pulled it up. Right there. Shop here at Sampson Community College, and I'm going to demonstrate a lab that that Victor and McGill had wired up and tested before the virus hit. And for those of you that didn't get a chance to do this, I'm going to take you through the wiring and programming of this PowerFlex VFD, PowerFlex 4. Take you through the wiring, programming, and some testing and doing some measurements with a meter and a scope meter as well. So we'll start out by showing you the drive itself. And you'll see my camera's going to have to be moving around from time to time to get everything in. Okay, so this This is the drive itself, the VFD. Now let me ask you, and I'm going to pause it right now. So everybody hears audio. How does the picture look?
It's a little choppy, but we can see it.
Yeah, you can still see it though.
Yeah,
Now-
we can see it.
So how many people, is there anybody in here that did not get the program and wire that drive? I'm going to click out of screen share real quick and see if
I didn't.
you did not. Okay. So that's enough. That tells me enough right there. So let's go back. Okay, so screen share. There. Jameson, I think you did the saw starter, but you didn't get to do the VFD. Okay. 4, that's the cover that would have went on it right there, and I took the cover off. So it's a PowerFlex 4. They also make 70s. They make 525s. The newer ones nowadays are popular are 525s, 523s, and 525s. But these are still popular, still used a lot, say at the Butterball plant and maybe at Smithfield possibly. They do last a long time, so they'll be in service. I'll upload this tonight so that you can see it clear directly off of YouTube. It's gonna the quality is going to be better when you see it directly off of YouTube. But it's a slow process, so you'd have to wait till tomorrow to see it if you were going to go back until they fail, and then they may replace them with with higher models possibly. But anyway, so again, that is a drive, and I'm going to switch over to a screen share and discuss the wiring. Well, actually, it may be better off just to actually hold the drawing and then trace the wiring as we go through. So if you look right up here, I've emailed y'all the quick start guide. This is the quick start guide, and it's in your email. I sent it last night, so you have a quick start for this PowerFlex 4 and a user manual, which is a lot thicker. The quick start guide is only it's only 11 pages. Yep. So it's a very good thing. You really, yep.
Oh shit, he's doing it. Derwood.
Yes, sir.
Hey, this is Darren. I'm here with Justin. I was just gonna let you know we all watching this.
I was wondering.
Yeah.
I didn't know if I need to send the sheriff to go find you or what.
No, I'm here. I watched the Tuesday night too.
Okay, good.
Yeah. All right.
Hey, does this sound familiar?
I hear a drill.
Y'all ain't by any chance hear that last week or Tuesday?
Hear what? That drill?
Yeah, did y'all hear that Tuesday on the computer?
No, I didn't.
Oh, well, I hit the unmute button by an accident. And I was using the drill. I was working while I was watching this, and Daddy said he could hear it in there on the.
Well, how can you learn? How can you pay attention and you're drilling something? What are you drilling?
I was working on the 4-wheeler. I was listening.
Now look, come on now. All right, y'all ready?
Yeah.
You need to read the entire thing. Won't take you that long, and you'll be glad you did. You'll really learn a whole lot in that. Get that off your email and put it on your phone. Download that quick start. At least it's not so big, but it's got most of what you'll ever need right on that. I've got it on my phone in that short document there. You can also save this PDF I sent you to your smartphone. It's the best place to put it. You should put this on your smartphone like I have got on mine, and you've always got it because it has on there. It shows you the wiring, how to wire and program, and it gives you all of your common parameters. So we're going to start out with the wiring first. Your power wiring is going to be on page 4 where it says English 4. And just very simply, you have on a 3-phase drive, if it's 3-phase coming in like this one is, your 3 leads come in on the L1, 2, and 3. And then your T1, 2, and 3 actually goes to the motor. And then your ground leads, your motor ground would go here, and then this ground would actually go to your main ground bus in the machine. So that's your power connections. If you had a brake resistor, you would hook your brake resistor to BR plus and minus if you were using dynamic braking. If you had to stop real quick, and we're not doing that, we're actually ramping when we stop, so we don't need a brake on this. So we flip over, and again, the wiring that Victor and McGill did, they've already brought in the 3-phase. They brought the 3-phase in down to here. All of that's already been brought in down here, and then the 3 phases are leaving, and it's going down to that strip right there, they're going down to the motor. The motor's right down there. You see it. Well, I'm going to let you see it running a little bit. So anyway, the wiring is correct. Now let's talk about the control wiring real quick. So the control wiring, those of you that did not wire the remote controls on this drive, look closely, because I know that Costa and Alex, they did the basic startup of just bringing 3-phase in and 3-phase leaving, and they ran it from the keypad, but they never did get to finish doing this part. So if you guys are watching the recording, look close. This is what you were actually getting ready to finish before we got out of the college. So watch closely. It's simple. The control wiring is done on that strip right there and then the one under it. So the picture of this one and this one I'm going to show you here is, this is the picture on page 5 of your quick start. Shows you the pictorial of those two. So that strip and that one right there is terminal 1 through 6 and 11 through 16. That's 1 through 6, and then on the bottom 11 through 16. So here, what we're doing, we're wiring. We're using sourcing type wiring, SRC, instead of syncing. For sourcing, you take 24 volts down here that's inside the drive. They have a built-in power supply within the drive. But let me double check, make sure that my mic is actually recording well. Okay. 1, 2, 3. It is. Okay, we're fine. We're fine. Okay. I was concerned about the mic. Was it recording me? So anyway, so back to the diagram. I'm going to try to make this quick because I know you guys are, if you're watching this at night, then you're getting tired. So anyway, so when you're doing sourcing wiring, SRC, as compared to syncing wiring, we're talking about our field devices, our start button, stop, reverse switch, or any other special inputs. And basically here, we're taking 24 volts that's within the drive on pin 11. It's got a built-in 24-volt power supply. We're sending 24 volts out to the stop button, the start button, and the reverse switch. 24 goes through those field devices into the drive. So the drive's actually looking for 24 volts coming in. That's called sourcing wiring, because your field devices are actually sourcing 24 volts coming into the drive. And if you're going to use this convention of wiring, SRC, then you need to go down here on this switch down here, that little switch that says sync and source. Syncing, SRC, you put it in the down position. So that switch is, I'm get the camera like really close to it. Can y'all also hear me talking?
Yeah.
Good. Yeah, this Zoom is a lot better. You can do, I got double audio sources going to you. Get a light where you can see what's going on. Yeah.
I was just trying to look at your video on YouTube and it says it's private, so we can't see it. Sorry.
Really?
Yeah.
So I have to go in there and undo that. I'll have to change that. I know when I send you the link.
I don't know if you can read it or not. But.
Well, I have it.
Sorry.
That's okay. It's a learning curve.
Yeah. I was just trying to look at that because we had already wired that already. So.
Right. Let me make a note here.
Okay.
So I want to make YouTube. I guess it would be public versus private. See, I'm learning. I'm learning about setting that stuff up, and it's new to me. The lady in charge of Moodle at the college, the one that told me, she said, listen, you put your stuff in YouTube and be done with it instead of trying to send Zoom links. So I did that, and I had to get an approval from YouTube to upload videos longer than 15 minutes.
Right.
And they checked me out, and they said, yeah, I can put them in there now up to 128 gig. So they said, I thought mine are averaging 2 gig or less, for like 3 hours. So it's okay. So I'm fine now. But I'll figure that feature out tonight. I'll get that straightened out.
Yeah, I think there's a public and there's a private, but I think there's a way that you can let certain people look at it too, I believe. But anyway, okay.
Well,
does it show a picture of what's in the video?
No,
So it's just kind of like a blank screen.
Well, I just tell you this video is private. That's all you see.
Okay, all right. Does it tell the name of the video?
Hold on, let me go back to it.
Yeah, it's okay. I'm gonna let this play here while that little switch right there.
Yeah, no, it don't.
In the down position, it doesn't tell the name of it.
I don't know if it'll focus or not.
Yeah. I'll straighten that out tonight before I go to bed. I'll get it straightened out. This has just really got all of us in a whole nother mode of living, man. But at least we're still living, right? You know.
Yeah.
So, okay, I'm gonna let it roll here. You can see right beside of it. It says SNK on top, and then SRC at the bottom. So we want to do sourcing. That's what we've got. I know the reflection is bad on that switch. It's a real small switch. That's why I'm showing it to you, because I think you can kind of see it pretty good right now. You can miss that. That's it right in there. And it's a little itty bitty little switch there, and that can make the difference between the drive running and not running, based on what configuration are you going to do on your wiring for your push buttons and all. So anyhow, you back out and put my light up here. So coming back to our paper here, let's talk about the wiring. Let's walk through it real quick. So you have the 24 volts. We're taking pin 11, and we go out to our stop, our start, and our reverse switch. And each one of those has a separate input going in. Stop goes to input 1, start goes to input 2, and reverse switch goes to input 3. So I'm just going to show you where those devices are real quick. Now, we're taking here, right under here, we're taking the pin 11. I'll get this here out of the way. This is pin 11 that's up under here, behind there. That's your 24 volt right there, the 24 volt. And it's actually going, let me get my oscilloscope out of the way here. Got a lot of stuff around here I'm juggling. So the 24 volts is coming right through here. The 24 volts comes right down to here. It goes to a double jumper set on the terminals. The 24 is coming right into there, and it doubles right there on that double jumper set. So the 24 is coming out to your start and stop. That's your remote start stop. The 24 volt comes out here to a normally close on the stop. It jumpers over, it feeds into the stop, and it also feeds into the start over there on a normally open. Okay? So it's feeding 24 in here, 24 in there, and then the stop has a separate signal leaving going to the drive, and then the start has a separate signal going to the drive right there. Okay? So we'll leave that open. The other wires are actually for the LED, for the lights that are in there. We'll discuss that last. But this is 24. This is a signal going to input 1 for the stop and input 2 for start. So let's bring the camera back out. And what you saw leaving the stop is actually there, and what's going to the start is input 2, okay? Input 3 is actually coming from the reverse switch. I'll show you on the door. The reverse switch. If I could have a camera, so here you have 24 volts going into the reverse switch, and then this here actually leaves and it goes to input 3. So I'm pulling on that one right there. You see that one there moving, and that's actually input 3 right there. So that's the one for the reverse switch. Okay, so that's got you on all of the on your regular on your 24 volt inputs. So three of your inputs are 24 volt. 24 here is stop, start, and reverse. Now, initially, let's move this back. Initially, let's say if you were going to run this drive here, if you were going to run it from the keypad, not remotely from external buttons, if you were just going to run it here on that start and stop and so on that reverse and run it locally from the keypad, then you wouldn't have any of this external stuff wired in. And you'd also have to have a jumper. A jumper would have to be installed that's actually factory installed between 1 and 11. So that jumper's in there. I had to take it out because I'm going to use an external stop button. I'm going to use a real one on the outside. If you're not going to use the outside, but if you're just going to use the keypad for stopping, you got to put 24 volts from 1 on 11. You see here? You go from 11 with 24 volts up to the stop input. So here, 11, a straight wire jumper from there, bypassing that going to 1. And that's what that jumper is right there. And it allows the drive to run with a stop signal that's hardwired externally. Because, a stop button is normally closed, as you see right here. So input 1 has to always be on. It has to have 24 volts there constantly, or the drive's not going to run. So that's the reason behind the jumper there. If you're not going to use any remote controls, if you're just going to run it locally from the keypad. Okay. So the next wiring would be the speed reference or the speed potentiometer, speed pot. The speed pot has 3 legs to it. It's a variable resistance in there. And so you take and you put, there's the 10 volt power supply within the drive. So pin 12 and pin 14 is 10 volts if you measure from there plus and common on analog, common on 14. Then you would measure 10 volts DC constantly there on pin 12, reference to 14. So you put 10 volts across the potentiometer, and then the wiper picks up some percentage of it, either a little bit or half or a lot, and it sends that percentage back on the wiper. That's a wiper like a windshield wiper on a windshield. So it's a wiper inside the pot that gives you a variable 0 to 10 volt DC leaving the pot going back in, 0 to 10. That's an analog signal because it's not simply off or on, but it can be 0 volts or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can be anything between 0 and 10 volt. And whatever's on that line is going to determine the actual speed of the motor. This is what you call a speed reference. The speed reference input is input 13 if you're going to use a pot. Okay, so that wiring is going to be this. You'll have a red wire here, a clear wire here, and then a black wire for common. So 12 is black, and then got black, clear, and then red, clear, and black. And so if you look up on the drive, you have here red, clear, and black. Okay, and then you have a 4th wire coming out of that. By the way, this cable here, this cable is a shielded cable for the speed pot. So it actually has a shield around it inside there, aluminum foil shield. And this drain wire right here is connected to the shield in there. I got heat shrink on that. They put heat shrink on that, and to protect it. It's a bare wire that's in there, and it's connected to a shield that goes around that cable inside to block noise. So the shield connection is right here. If you see the dashed line, that represents a shield that actually blocks noise off of that low voltage line. The shield actually connects down here to pin 16, which would be over here. So that's pin 16 there. That is that's your shield or drain connection. And then it's internally it's also grounded. So it's a ground connection for that. Okay. So three wires and then the shield and then because the pot is low voltage on 10 volts and that wiper coming in is 0 to 10, you got to have a shield on there because any interference within the panel could actually confuse that analog signal coming in, your speed reference. If you get noise induced onto that line, then the drive is going to get confused and you're going to get erratic speed responses off of the drive if you don't have this cable shielded. And by the way, you only ground it on one end. You ground it on the drive end, not on the pot end. So if you notice up here on this cable, we've got the shield connected over here to your ground. We have it connected there. But on the end, on the panel, I'm going to swing it around and come right around to here. On this end, we don't have the shield hooked up. We actually clipped it. We clipped the shield right there, and we're just using the red to clear the black on the pot. So the shield does not hook up. That fourth one, that protection shield, is not connected on the pot. It's only connected on one end at the drive itself. And that's to avoid ground loops, which is a kind of another deeper subject. But anyway, you only hook up the ground on one end on low voltage analog speed reference signals, like right here. Only necessary on one end, okay? It's kind of like a gutter. Think about a gutter that when you tilt the gutter and then the rain runs downward, you want the noise that may get induced on this to run in one direction toward ground. I think of it kind of like a gutter. You got to have it sloped and it's going to go in one direction down to the ground. So that's kind of a very rough way of saying it, but I mean, you can probably relate to that, I'm sure. So that's your wiring for that. One other thing, we have some lights. So the lights that are out here, the light bulbs that are in here, those light bulbs are actually 120 volt light bulbs, or rather I'll say this. The transformers here, they take 120, and they step it down to a low voltage 6.3 volt for that light bulb. But that light assembly right there where that transformer is, it has to have 120 coming in. So we want to have 120 volt for a red light and 120 volt for a green light. Now, since it's 120 there, those buttons are light, or those lights require 120. Then the VFD does not provide 120. Okay, but what it does have is it has a relay. It's an auxiliary relay that you can use and program for a number of things. And you can run power into that common wire for the relay contact, and have a normally open on the left and a normally closed on the right. And what we're doing is we're feeding 120 volts into the center terminal, and then we have the signal leaving here be 120 volt to the green light, and the one on the right would be 120 going to the red light. So on your same wiring diagram there on page 5 there in your quick start, here's what we're using. This is the internal relay. It has a common, and then it has a normally open on R1 and a normally closed on R3. So R2 is your common, and we're feeding 120 volts in, and then this goes to the green light, and that goes to the red light. How's everybody doing out there? Is this putting you to sleep, or is it okay? Or
No, it's good.
Oh, good.
Okay. Is there anybody out there that's still there that wants to see this part, or should I fast forward it?
Oh, we understand. I'll understand.
Is anybody, Jameson, you still there? How about Justin and Thomas? Are y'all still watching? I'm trying to figure out, should I fast forward? Is anybody watching it that needs to see it that hasn't done it? So that if I can fast forward it, then you guys that have done it won't have to see it again.
Yeah, I don't see Jameson on.
He's there, but but I don't hear anything back. I'm not sure if he's.
You can hear me, Joe?
Oh, okay.
I don't know who I'm listening to.
Thomas?
Thomas. Yeah.
Yeah, we good.
Okay. So you didn't get to do this lab, did you, Thomas?
I don't know if I done everything I think I done.
You didn't do the VFD though, did you?
I've done everything that was on the thing that I know of.
The drive that I'm hooking up there, do you remember doing that?
Yeah.
Yeah, they done the one on the opposite side of me and Pat, didn't?
Yeah, we done that one while we was still in the class.
Right. Did you hook up the remote controls on it?
Yeah.
Okay.
Me and Jameson and Justin who did that one up, I believe.
I thought Jameson told me a while ago that he hadn't done this.
No, I didn't do that one. The VFD.
Right. Okay, I'm gonna let it roll then. Y'all bear with me. Let's let this finish out. And I may
think that's the one we hooked up the last time before we left.
It could be.
That was the soft start, I believe.
Yeah, you were on soft start. But since where you're at, Jameson,
me and Justin. Me and Justin hooked up one in the tall panel.
Right. Yep. I think you guys might have, yeah, y'all did the half horse PowerFlex. You did the small one.
Yeah, right. me and Pat watched them when you tested theirs, then me and Pat done ours.
Right. I don't remember because I'm not sitting here looking at the grade book, but yeah, I do remember now though. We're gonna let it roll, and I may fast forward through some of it, but we're gonna let it roll because again, Jameson didn't get to do it, and if you ever end up in the electrical department, Jameson, you definitely need to see this. So we're gonna continue to let it roll here. I'm gonna hit, and we programmed this. That's your terminals there, that's in there, and that's your terminals right here. And we programmed the relay with a parameter that we'll get into in just a little bit when we get the programming portion of this. So anyway, so the physical wiring for the relay is going to be this. In this panel, and I'm back up the camera here. Okay. Now, so I think I've got some shadows here. That's back up some more. I'm trying to be a cameraman and everything at one time, guys. So it's a challenge here. All right. Okay. I think we're fine now. So here's the wiring scheme for the lights. We're taking the relay with either drive. That's an auxiliary relay that you can do different things with. In this case, we're going to let the relay click on when the drive's actually in motion running. So we're taking 120 volts off of the transformer here in the panel, feeding it to R2, and R1, R3 feeds a green light and a red light, and then we have a common going back to the transformer. So that's a very simple wiring there. It's 120 volts here going to the light bulb assembly, so the transformers that step that down. Okay. The light bulbs themselves are 6.3 volt, but there's a transformer within the assembly that I showed you, and the transformer steps down to 120 down to that. So within that assembly of the red and the green light, we'll take you back over to here. And this whole block here, that block is a transformer that accepts 120 coming into here in a neutral, and it steps to 120 down to 6.3 volts, and you have a very low voltage 6.3 volt bulb inside of there. But we considered that to be a 120 volt assembly because that's what it takes to actually, to feed the bulb on the primary side there. So, that's the reason for. I mean, I'm just explaining that the bulb is actually very low voltage, but the transformer takes your 120. So that's all the wiring. That is all the wiring. And so next we go over initial programming. Gray hair, man. Look at that gray hair.
Learned.
Let's get this up. Let's see what's going on.
You learned.
Yeah, with my camera. And I've got a better camera ordered that does auto focusing, and I won't have to do so much moving around.
Yeah,
while I'm programming, I'm going to put a cover on here, so I'm not going to run the risk on touching anything, because you have to program barehanded, you know. So we got our cover on there, and that I know the display's a little bit blurry. See if I can manage to find an angle that's not so blurry. No. If I had a camera, man, I would have been way smoother on this stuff, but you know, we don't. So
you can follow along though.
I'm trying to find an ideal location here.
Yeah,
so that's actually pretty good, right? There's a little bit of a glare, but it'll do what now?
I think for doing it by yourself, you're doing all right.
Well, I appreciate that. I'm trying hard, man. I swear I am. I'm trying hard as I can to get to all the best you can get, because you paid to learn, and it's just a bad deal the way things are. But again, you're able to see what I did today, and I wish I could have brought the drive home, man. But this darn motor in the back of this truck is not VFD rated motor, man. For those of you that came in a little bit late, all motors cannot handle VFD signals, VFD waveform. Yeah, so it's again, my plans didn't work out, so I had to do it in the shop today, and I filmed all the way up to like 1:30, man. I got in there at about 8 this morning, or was it about 8:30, and I filmed all the way to about 1:30, doing three videos in here with this stuff. So anyway, so here we go. It'll be on YouTube. I'll gradually have them all on there. This one will be on there later tonight. Work. So I
feel like you're doing a great job.
If you ever have,
yeah,
well, I appreciate it, man. If it weren't for the camera, it would really have me worried, man, because I knew when they said I could use a camera and showed me how to do it, I said, well, I think we can kind of get by, you know. And let me just say this also. I did have a student one time. His name was Daniel Smith. He works at Schindler in the electrical department. He's a very good technician. He took this class 2 times. The second time he took it, he actually needed another couple of credits to be able to get financial aid. He didn't need to take this class again, but he needed like 2 more credits to get financial aid. So he said, well, can I take it again and then start from where I was and keep going and do more advanced stuff? And I said, it's fine with me as long as they'll let you do it. So they actually let him take it a second time voluntarily, and that qualified him for financial aid, man, that semester. And I started him out where he left off, and he went on further. And so that's a thought. Next year comes.
I know, Daniel.
Yeah. So if next year, you can have that in mind, that if you wanted to take it again, you could do it and pick up from where you left off. And I'll tailor your labs based on where you left off. You know, I mean, I did that with Daniel Smith, man, and it worked out fine. I mean, he definitely went further than the rest of them for sure. So
you should have like another motor controls, like more advanced class.
Right. Yeah, I could teach it. We just need to get more equipment, and it needs to be designated as another class, because the textbook that you have, this motor control book, can absolutely cover another semester. Ain't no doubt about it. So
that book goes a long way for the one.
It goes a long ways. So whatever you do, don't never get rid of that book, man. You keep that book. You hold on to that book, because you can keep growing a lot within that book. And if you ever have questions beyond the class, you can get up with me. I mean, I'll help you beyond this class, that because of after the exam, that's not the end of me helping you. I'll help you as long as I'm breathing. Okay. As long as I'm breathing, you can get up with me and I'll try to help you with anything motor control or PLC wise, and I'll do my best to help you. So I'm going to let it roll here. We have a VFD that's giving problems that's previously been doing fine, and all of a sudden it's not doing well, and you wonder, and you're thinking you may have to replace the drive. Well, before you do that, before you replace the drive, here's a thing that you can do, a safety that you can do. You can go to a parameter, and this is on page 9 in the quick start. Everything I'm telling you is in the quick start, which is a wonderful little document there that's got so much in there. And I emailed it to you. This section right here has all of your basic parameter group. Sorry about the camera moving around. Page 9, it has in here all of your basic program group. It has where you're going to program and tell the drive what the motor nameplate volts is, the hertz, and the current for the motor, minimum frequency, maximum frequency. Those are the parameter numbers right there, and so on. At the bottom, you have. Can y'all read that writing? Can y'all actually read that writing?
Yeah.
Yeah.
Okay. It's telling me that's just confirmation that it's worth doing if you can read it. Okay. Have something called reset to defaults. Parameter 41, if you enter a 1 in there, it's going to make the drive go back to the original factory settings. It's going to clear out any bad information that someone may have done by accident. The reason why I show that, guys, is because a guy at Butterball told me he's actually found VFDs that people took out of machines and they throw them in a trash can because they tried to get the VFD and the motor running right and they couldn't. So they just assumed the VFD was bad. They pulled it out and threw it in the trash can and put another drive on there. When really what had happened in some of those cases is this guy that told me this, he said, now I go around, I get them out of the trash can. I'll actually reset them with that setting there, parameter 41. It clears out any junk that's in that drive. It clears out all parameters that anybody put in there, and it recalls the factory settings just like it come out of the box. So it will absolutely do a clean sweep in the memory in that drive. And if it's a parameter bug that they put in, a mistake, this will straighten it out in about 2 seconds. And then you put your custom parameters in for your application. So if you watch closely here, this is how you actually clear out any junk that somebody could have got. Some people are too prideful. They'll get out in the woods and they get lost and they get further and further and further, and then they want to throw the drive away. You know what I mean? Oh, the drive is no good, and they're too proud to say, well, I just didn't know what I was doing, Y'all ever met anybody like that?
Oh, yeah.
They'd be lost and wouldn't tell you, wouldn't tell nobody, and just throw the drive away, because they're just too, they don't want to say, well, I'm not sure what I'm doing, So we're going to go into the parameter 41 real quick, and we're going to actually default the drive and let you see what happens when we do that. So what's that? What was that? I'll go here. So we go back to here. And to get into the drive, you can hit the escape button. And when you hit it, if it doesn't blink, that means that you're all the way out, and to get back into the menu, you have to hit enter. So you can start out by hitting escape, and if it doesn't respond, that means that you're at top level. You get back in by hitting enter. So now you're seeing a P flashing there, and the possibilities of what's in that first position would be one of 3 things. And I'm going to show you the 4 letters that could show up there. So where the P is flashing at, you could possibly see a D for display group, view only or read only things. P is basic parameter group. That's what you're seeing now. A is an advanced group, or F is fault, is going to be for a fault code. So those letters can show up in the first position. We're going to scroll through there. While the P's blinking, if I hit up, it's going to take me to the advanced group. If I click it again, it's going to take me to the display group where I can choose things to view while the drive runs, like output voltage or frequency. This is like a display only group, read only. And you hit it again, and it just cycles back around from D to P to A and back to D. Now, for it to say F up there for fault is if it generates a fault, it'll say F. And then you go to, if you happen to get an F there, then you simply go to the last page in the quick start. And the last page gives you, page 11, gives you all the fault codes. So whatever F number it is, it's going to tell you what it is and what what you could possibly do to remedy the problem. But here you have fault number F2 through a F122 that's shown there. And so that's a very handy thing to have. If you put this quick start in your phone, you'll be good to go. So to reset our drive to factory defaults, we're going to do this. We're going to parameter 41, and we're going to put a 1 in there. So I've got to go to P. That's the P group. I hit enter to get into the P group. And then the cursor moves over there. Now I'm inside the P group, and I can move it over to 41. I go to 41, and now I hit enter. And it has a 0 in there right now. I'm going to change it, hit enter again. Now it starts flashing, and the program LED comes on. That means I'm in program mode. I can change it. I'm going to go up and hit a 1. And then to accept it, I hit enter. And when I hit enter, it actually generates a fault 48 that's telling me something. So what does fault 48 mean? It's good news. It's telling me that the parameters have been defaulted. The drive was commanded to write default values to a EEPROM, which is a memory chip inside. To clear this fault, you can clear this fault or cycle power to the drive, and then you program your parameters as needed. So what we've done here is the fault 48 is confirmation that the memory in here, the user memory of parameters, has been cleared to factory settings when it was brand new. You hit the stop button to clear that. And now this drive is set back to factory settings like a brand new one. So at that point, it will run from the keypad. As you notice that the start button is illuminated, and then the speed pod is illuminated. So it can be run from here, not remotely at the moment. Before you run it and test it to find out is the drive okay whenever you ignore external controls, before you hit the start button, there's 3 pieces of information you want to put in there. You want to put in there the nameplate voltage, the hertz, and the frequency that the motor can accept. So here we're going to put in parameter 31, P31 for nameplate volts. We're going to put 208 in there. And for the hertz, it's 60 hertz that the motor would accept. We put 60 in there, which it's already 60 by default. And then under overload current, what we do is we actually put the current rating of the motor on there, and then it actually it allows extra. You don't have to multiply by 1.25 like you do on a regular starter. It will actually give you that extra 125% or so roughly before it trips. So you just put nameplate current in here. And the nameplate current on this motor here happens to be 9 amps for a 3-horse motor here, okay? So I'm going to put 208 in here, 60 in here, and then 9 in there for amp. I just stopped it. Now for nameplate volts, if your panel has 230 in there or 240, then that's what you're going to put in that slot for parameter 31. You're going to put the actual voltage that's in your panel. So let's do it. Let's go to parameter 31. So we hit escape. Now we're going to hit enter. We're in the P group, and we're going to parameter 31. So we go to 31. We got to get over here, so we hit enter to move the cursor, and then we're going to 31. 31 and enter. It says 230 by default. We're going to change it to 208. So we're going down. If your machine's running at if you have 230 coming in, you're fine. But we're not. We're actually have 208. So we're telling the drive, so it's going to know exactly what's going on, and you get the best performance out of it. So next we have parameter 32 hertz. It's going to be 60 hertz, and it's already set that way. So parameter 32, go up, 32. It's already 60. We're going to leave that alone for hertz. Escape, and we're going to go to parameter 33. Parameter 33 is where you put your current in. I'm going to put 9 in there. Hit enter and go down to 9. If you look on the nameplate of the motor, that's what it's telling me at 208. Hit enter. And by the way, just so you'll know, the camera's going to shake a little bit here. So just overlook that briefly here, guys. It's going to move. We're going to take you down to the nameplate. Let me get my monitor where I can see better. I'm showing you the actual nameplate on the motor. And I'll be glad when I get a better camera that focuses by itself. See if I can do one more maneuver here. Bear with me on the camera movement. I'm trying to get where I get a focus here.
This is a bumpy road,
with a camera that does an autofocus.
But we're rolling though. It's bumpy, but we're rolling.
So if you see,
all right, look closely on that plate there, guys.
All right, that's fairly decent right there. You see the 9 amps right there? 9 amps. When you're at 208 volt, it's 9 amps. At 230 volt, it's 8.4. At 460 volt, it's 4.2 amps.
Can you actually read that, guys?
Yeah.
Okay, good. So the motor, as you increase the voltage now, that the motor doesn't guzzle as much current. Basically, it's like a vehicle that, the more voltage you give it, the less amps that it wants. So but these numbers, whatever voltage you're at, you got to be careful to put that specific number in for your amps and that specific voltage if that's what you're running at, so that the drive is going to give you the best performance for that motor. We're going to take the 9 amps at 208, and that's what we're putting in for our running amps. So this comes right off of the nameplate of a 3-horse motor down here that we're going to be running here. So it's very important that you set drives up to match the motor. So there's no way for the drive to know what you have. You have to actually tell it. Okay, go back. And now, so that's where the 9 was put in. And so those 3 parameters is enough to actually manually run the motor. And by the way, there are 2 parameters that I put in there that are very, very long already. I'm just going to tell you about. I'll go ahead and show you. Down here in the basic group again, the same group here, you got to the bottom for parameter 39 and 40, it's acceleration and deceleration. That's the amount of time that it takes when you hit the start button to go from a dead stop to full speed. You can go from 0 to 600 seconds, and also on deceleration, the same thing. I've actually got it set on 30 seconds right now. So we're going to go and look at 39 and 40, okay? So go up. But actually, when I defaulted it, it's really on 10.
And let's hit out, and we're going to go to 39.
You're getting ready to see that.
Hit enter. I've got, well, actually, the default settings are 10, so it's really on 10 right now. I'm sorry.
Because I defaulted the drive.
The default settings, the factory settings,
over there on the right.
So for acceleration time, your factory setting is 10 whenever you default the drive. Same thing on deceleration, it's 10.
So the good thing about defaulting the drive, fellas, is this. It's going to put you back to square one with some good parameters that are like average parameters. And anything that somebody could have got lost in there and screwed up, like maybe in here for speed reference or start source, it's easy for somebody to get it in the wrong place and mess it up and not even know they've messed it up or not admit it. When you default that drive with that parameter 41, you're going to get rid of any crap that's in there. And it's going to, if there's nothing wrong with it physically, it's going to run. Because that, again, that's a very important thing to do before you replace a drive, whenever you default the drive. So it's at 10. It's going to take 10 seconds for it to go up and ramp up or ramp down. I go back out, escape all the way out. So now I'm going to hit the start button here, and you'll see it take 10 seconds there
for it to ramp up. I'll get my stopwatch out. We'll do a quick little test here. I'm going to put a scope on it in a minute or two, and you'll see the output like it showed in the book. You're going to see the square wave and how it modulates. Go into here. So if you hang on with me, you can take your you'll see something. You can take your phone and go into clock and hit stopwatch, and I'm going to have the stopwatch. But I can't really hit them both at the same time. This is not going to be really accurate right there. When I hit start, I'm going to see if I can do it that way. It ain't going to be one of you guys here. So I'm going to hit start and go at the same time right there. So if you see that, now when it levels off at 60 hertz there, I'm going to hit stop. That's the hertz right there. It was 60 is max. Bam. So it stopped at 10 seconds, as you see. That was the ramping time. This is the frequency that the drive is putting out to the motor. So it took 10 seconds to go from a total stop to full speed. Now I'm going to hit reset on my phone here. I'm going to hit stop, and I'm going to time the down or the deceleration. We're going to time that also. So I'm going to go here and hit stop.
I messed up on my phone 2 or 3 times. I messed up.
But I think I hit the wrong button over here. But you see it going down. The speed's going down. Let's go back up again.
I finally get it right here in a minute.
Now I'm going to show you the motor shaft in just a second. So if I can manage to do this at the right time here, I'm going to hit stop. Oh, Lord, I messed up again. Start. It's going to be off a little bit, but when it goes down to 0 hertz, I'm going to stop this. Bam. So 9.81 seconds. I was a little bit off. I hit it late. You can figure 10 seconds as far as the deceleration there. Okay. So it does what we say it's going to do. And then also, now let's take a look at the motor shaft. So we're going to move the camera real quick down.
Thomas, I put some red tape on there for you. You'll see the red tape on that shaft, Thomas, if you look real close.
We give you that idea, Darwood. Huh?
Did what?
I said, who give you that idea?
You did. That's a Thomas right there. That red tape. Watch that shaft.
Okay, so there goes your shaft right there. Now I'm gonna hit the button, and then you watch it start out real slow. 1, 2, 3, go. See, it's going real slow there, and it's gradually speeding up. Could y'all see that? And now it's actually at 60 hertz.
It's the
I'm going to
fast.
hit stop, and you'll see it deaccelerate very slowly. You see it slowing down. You'll start to see the red tape on there, Thomas. I did put some tape on there.
Y'all see the red tape?
And so there you go. It starts very gradually and it stops very gradually. And your ramping times, of course, can be changed according to what your process needs.
Were you able to see that?
And
you were. Okay.
So there you go with that.
I'm getting ready to put a scope on it and a regular meter. So hang on, just keep watching. You're going to see something that's pretty interesting here.
Come down. And now what I would say is we're going to look at some voltage measurements real quick before we close the lab. Well, actually, we're going to do more programming. When we defaulted the drive and then we put in the nameplate voltage, the current, and the hertz, it runs from the keypad, which is called local. Now we want it now so that it's not going to run from here, but we want it to actually run from these buttons over here. We want it to run from these controls here. So we're going to put this back in here, close that up, and we want this start and stop to actually run it, and we also want this speed pod on the door to run it, and we want this forward and reverse switch to run it that's on the front of the panel. So these remote controls have already been wired in. We've already traced it. And so let's do the programming so that the drive will actually pay attention to those controls. So So we're going to put the cover back on, okay? And there's just a few parameters that we need to put in that'll take care of that. Just a few more, guys. Hang with me, and you'll see some good stuff for the benefit of whoever didn't get a chance to. A lot of you didn't get a chance to do this, and I regret that. But the virus hit, and we have no control over it. So, anyway, let's go back. So the parameters that we're going to be looking at are going to be this. We've already done nameplate volts. We've done hertz. We've done overload current. Now you could do minimum, maximum frequency. If you did those, it would tell you the minimum frequency the drive would ever run at or the maximum. You can do that if you want to restrict it. Now, let me tell you this. Any of you that are working with pumps, if you got pumps that are running on the VFD, Guy Butterball told me he found out these were brine pumps that are pumping salt solution through some injectors, and they inject it into the turkey meat for their process. He had these pumps that if he run them at 60 hertz all the time, something was mechanically wearing out in that mixing tank. And with the pump system, something was wearing out mechanically. He decided one day just to ease that speed down a little bit to about 50. He did that, and it actually solved his mechanical problems. Something in there that was wearing out premature. It cut way back on things wearing out in that pump system when he changed the frequency from 60 just down to 50, and he didn't lose any. It didn't affect the production rate any. So it's just a thought. He went in that parameter right there for maximum. He put 50, and that's all he did. So it's little things sometimes. If you think about all of these features that are in there, you can customize them to your application and maybe solve some problems on your process where you're at. It can be easily done. And no matter what the speed pot's set to, it will never go above that maximum setting or that minimum. You can actually set your sweep min and max here. Now, but we are going to adjust, we are going to set the start source. Start source is, are we going to run it from the keypad? No, we're not now. We're going to run it from a 3-wire. We're going to run it from a 3-wire control source that consists of a start button and a stop button. So why does it say 3-wire? And we put a parameter 1 in there if it's going to be 3-wire control for start source. Well, if you flip back, look at your wiring. The 3-wire meaning comes from this. Is you have 24 volts here, that's 1 wire, that's 1. And then you got a stop wire and a start wire. So that's 1, 2, 3 wire. It's a 3-wire start source involving 24 volt, a stop, and a start signal, total of 3 wires. So that's what you got to tell the drive so that it'll pay attention. So it will actually be looking at for stop and start in that manner versus a 2-wire. If you were going to have a 2-wire input, it would only be one normally open contact, not 2 devices. So if it was going to be a 2-wire input, which it could be, then you would simply be using input 2 there, 1 wire here and 1 wire there. You'd have a jumper on there for your stop. You'd have to go back in there without a factory jumper for the stop input, and you would have a contact there feeding input 2. That would be a 2-wire input only, maybe from a relay or a PLC output. So that would be 2-wire versus 3-wire with 2 devices, okay? All right, now, so go back to our parameters. And so we're going to put a parameter of 1 in parameter 36. 36 needs to equal 1. So let's go up here to 36, and we go into enter, and enter again to get the cursor over. We're going to go down to 36. It has a 0, and we're going to put a 1 in there. And now it's going to listen to, the external pot, not this one. You see that light went away? because now that start button is not going to be active on the keypad. If I put a 0 in there, that'll light back up. So if you watch it, I put 0 in there, hit enter, that lights back up. Now this is going to be the start source, not the external start button or start button. So let's put a 1 in there. It's going to listen to the remote now. Okay, so what else are we going to do?
Speed reference.
Our stop mode.
Oh, stop mode, yeah.
Our stop mode, we want it to be ramping for stop mode and also clear fault. So when you hit the stop button, it's going to ramp the stop, and also that same red stop button will actually clear a fault. CF means that it'll clear a fault. So let's put a 0, and 0 is the default. It should be in there already, but check parameter 37 for a 0. So we check 37, and it has a 0, so you're good to go, okay? And then a couple more parameters, and we're going to run it, and then do some voltage testing. So the next one is going to be speed reference. So for speed reference, you can have the drive pot that's built into the drive. If you have it set to 0 for parameter 38, it's going to listen to this drive pot that's up here. So if you see right now, that potentiometer there is actually green. It's listening to this one now. So it's listening to the one on board, and that's not what we want now. So let's go to the speed reference here, and let's put it for 0 to 10 input. 0 to 10 input would be a parameter 2 in 38. So we go to 38, enter, and we're going to put a 2 in there. 2, and all of a sudden the pot's not lit anymore. So it's not going to listen to that at all. It's going to listen to the external pot that's over here on the door, which has been wired right here. This speed pot right over here, that one right there, that's the one that McGill and Victor wired. So that adjustment there, that's the one that's going to listen to now. If you go around the front, that's our speed reference now, not the one built into the drive. Let's go ahead and put it wide open there. Okay, we're almost done with our special parameters here, almost. And let's see what else do we have here. So we had our speed reference there. Let's move this. The acceleration and deacceleration is going to be now. Very briefly, I'm going to switch over to the data sheet. Do y'all see that data sheet show up there?
Yeah.
That's a quick start. Now watch closely here. I'm going to shoot down to that same parameter sheet on a PDF. This is what I emailed y'all this that document right there. And I'm telling you, it's small. It's not going to take up much space on your phone if you put it on, or you'll be glad you did. If you got these kind of drives.
I got it already.
Yeah, great. So yeah, it's whatever kind of drives you got in your plant, just download these a quick start, and you will be glad you did, because it'll have stuff in there that's just so hard to remember. So let's go down to enlarge a little bit more. Now, if you notice right here, can y'all see that good on start source?
Yeah.
Now, so for start source, if it's the keypad, you put a 0 in parameter 36. For 3-wire, you put a 1. For 2-wire, you put a 2. Now over here. Oh, wait a minute. We're on speed reference. I'm sorry. Speed reference. Parameter 38. If it's going to be the drive pot, the little potentiometer, it'll be a 0. If you're going to have a 0 to 10 input, like from an external speed pot, you put a 2 in there. 3 is something that we didn't talk about. It's a 4 to 20 milliamp input. Now, if you have a PLC that's actually sending a speed signal into a drive, it's more than likely going to be a 4 to 20 milliamp range signal from an analog output on a PLC. You'd have to put a 3 in there in parameter 38. Now, milliamp signals are used versus a voltage signal if it's going to be a long distance between the PLC and the drive, because current signals like that, you're not going to lose any current between the source and the drive. Current, no matter where you measure that in the loop, is going to be the same all the way around the loop, but you will have voltage drop if you're measuring voltage a long distance, but you will not have a current drop. So that type of a current signal is what a PLC would put out more than likely, and you got to put a 3 in there, and that's what the drive's going to be looking for. If you're going through a communication port on the drive, a network, you put a 5 in there, and that would let the drive listen to a network cable instead of looking at any of these other ones. Does that make sense?
Yeah.
Okay, good. So again, the quick start is really good source to have, and we're going to let it roll. Your preference there, based on your process. So, whatever you prefer them to be for your best production performance, you would set acceleration, deceleration according to that. Okay, and then one more special parameter here. We program the relay. And I'll show you how do you know where to go to program the little relay that runs those lights. So inside the drive here, that little relay that's going to run out, that's running our pilot lights outside, the relay has to be programmed. So the way that we find out where to go is like this. When you look here for the relay terminals is R1, 2, and 3, which is right here. Now you look that up down here, and it says for these terminals, these signals here, you're going to go to parameter number A055 is your parameter that actually sets up the relay function. When does it click? You go to advanced parameter 55. Okay, so we flip over into the same document here. And we go back to, we don't go to the regular P parameters. We flip over to an A group that's advanced. It's just the back page there. And again, I did email this to you guys, so you've got it and you can put it on your phones. So parameter A, this is the advanced group on page 10. And A055, it says relay output select. We want the relay to click when the motor's running. So we're going to put a 2 in A055, and it'll click when the motor's actually running. You could make it click when you have an overload. It's your choice. When do you want the relay to click? When it's ready or fault, or we want motor running. So we're going to put a 2 in A055. And then we're getting ready to run it, and I'll show you the oscilloscope. So we come over here. It'll be worth looking at. And you got to get the cursor all the way over here to P, and then rotate to the A group. That's the A group. That's your advanced group. And hit enter to get the cursor over to get deeper into the group. And now go 55. 55, and it's equal to a 0. And we said we were going to put a what in there? We're going to put a 2 in there for motor running. So we go up to 2, bam, and we've got it. Now, that's it. We're done. Escape all the way out. And now let's see what happens now. When I hit the button, let's see what happens. Nothing. It's not going to listen to this because it ain't lit. It's looking for an external. It's looking for an external signal now, like it's supposed to be. So if I go out here now, there goes your drive. There goes your button. Now watch. When I hit this, right there, now you see the drive starting to move now. So I had to hit the external button for it to actually recognize it. And it's ramping up. And it's up at 60 hertz, okay? That's actually, if I change the angle, you can see that a whole lot better. I'm going to hit stop externally. I think the internal stop will also work. The stop will work here, but the start will not work. The start won't, but the stop will. And it's ramping down like it's supposed to. Now I'm going to also that stop button functions as a reset or a clear, so that stop button has to be active at all times. You would never be able to disable that stop button because it functions as a stop, but it functions as a clear, a fault clear. Hit start again externally, and it goes back up, so it's ramping. There, and I'm going to hit the external stop, the external one. There you go, right there. So it's stopping. So it is listening to the external controls. And then the next one we're going to check is the forward and reverse switch. Okay, now this is a forward and reverse button right here that'll let you go forward or reverse. Let me see if I can change the angle here. Rocky road, but we're rolling. That's the forward and reverse button that works if you're going to run local. But we're not doing that. We have a reverse button here on the panel. That's forward and that's reverse. Now watch. I'm going to be while I'm doing that, I want you to look at the panel at the lights. You see the LED change on the left. So watch the LED over here. You see forward, the forward light, and then a reverse light. So it's actually watching. That's reverse. That's forward. Now I'm going to leave it in forward and bring it down to the motor shaft, and let you see what happens when I actually switch it to reverse while it's actually going forward. So now I'm gonna hit start. It's going actually clockwise, isn't it? Now I'm gonna hit stop. Well, actually, while it's running, I'm going to hit reverse. So yeah, right in the middle of it running, if you switch it to reverse, if somebody accidentally does that, I flipped it to reverse. It's going to ramp down. You're going to see it slow down, and then it's going to go counterclockwise. So watch it. It's slowing down clockwise. Now it's going to reverse. Now watch it right now. It's going counterclockwise now. So it ramped down instead of actually having a jerk reaction and slamming in reverse. It actually reversed by ramping. And if I hit stop, it's going to ramp down like it's supposed to. Okay, now from a dead still, I'm going to leave it in reverse and let it start. It's going to go counterclockwise. There you go, right there. So that's reverse. That's good. So with the drive, you don't have to switch the wires. You just hit a button. We're going to do a couple of measurements here with a meter, and let you see what you're reading. What here. The signals look like going into the drive and what it looks like leaving. And the other meter. Watch closely here. So we go. Let's see. While I'm getting the meter, while I'm getting the scope in place, I want to check to see how many people are still with us. So we've still got Victor, Thomas, Patrick, and Justin and Jamie. Okay, good. Okay. I'm going to share screen again. Let's see. Watch this screen here. That's a handheld oscilloscope you can buy, and they're roughly around $3,000. But every company should have one that you can share. This is a scope meter that's going to show you the waveform plus the digital up here. It'll tell you the voltage and the frequency in hertz that it's doing. That's plus it'll show you the waveform.
Hey, Darwood.
Now, first of all, sir. If we take a look at what's going into the drive.
Can you hear me?
Yeah, I hear you.
Darren's here with me and Justin.
He knows. We done told him. Yeah, he knows. I told him all day.
Yeah, Darren's there to keep you straight.
I got him.
We had to get him to come over here. He ain't got no signal around his place.
Huh?
He ain't got no signal around his place. He has to come over here to get online.
Okay, that's good. Well, that was nice of y'all to open your house up like that. That's great. That's great, man. Okay, what's good here? Watch the scope, guys, and wherever you end up working at, if they ain't got one, tell them to get you one, because it's worth. You can diagnose things with this that you can't do with anything else. So watch close. Don't miss any of this. Right now, the 208, it's going to be nice and clean sine wave. So what's actually going into the drive right now is that it says 211 volts RMS at 60 hertz, and that's a nice clean sine wave. That's what's actually coming in from the power company. Can y'all see that? That's nice and clean. That's perfect sine waves right there. Okay, that's what it's supposed to look like. Now, leaving the drive, Lead the drive. Look close here. This is very interesting. I want you to look at how vastly different it is. You're going to see a square wave and you're going to see it change. So with the ramping in place, I'm going to actually increase the ramping. I'm going to go to parameter 39 and make the ramping be like way longer so you have time to see it. I'm going to slow the ramping down so you can see it, the frequency change. And you'll see it modulate I'm going to make it to be 30. As it ramps up. And you'll be able to see the hertz change and the voltage change. Appreciate you guys sticking with me this long. That display's got it's worth it for those of you that don't know this information. So I'm putting on 30 seconds right here on ramping. So I put 30 seconds in for ramping. So your screen has time for 39. I'm going to go to 40 for deceleration, and I'm going to change it also and make it be like really long so you can have time to see the meter respond. The video, when you're seeing on the internet, we have to have things moving slow or you're not going to catch it. Right. That's what I'm finding out, guys. The response time is slow. I got to keep things on this broadcast. Not too fast. 30 seconds on acceleration and deceleration. So you'll have time to actually see the scope. Now, this is it. Very interesting right here. All right. So now I've got my probes here where the motor, where it's going to the motor at. And if you watch here, I'm going to hit the start button. It's actually down in millivolts right now, MV for millivolts. So it's auto ranging in millivolts right now, which is it's just picking up a little bit of static in there now. But watch closely there. I'm going to hit start, and you're going to see it start out real slow. 1, 2, 3, go. Now look at the square waves that you see in there. You see the square waves? Yeah. And you're going to see them actually kind of compress in like a spring. And you're at 140 volts, and it's going up, and the frequency is 24, 25 hertz. The voltage is now 167 volts. Frequency is at 35 hertz, and you see it keeps compressing like a spring being squeezed. This is your frequency leaving the drive going to the motor. 50 hertz at 219 volts, and now you're at 60 hertz. You're at 60 hertz at 234 volts AC, roughly. Now, that's kind of this is a square wave, and this is what the VFD produces. What you're seeing in our book is something like this. The VFD does not produce sine waves. It actually produces an artificial signal that's a square wave that has a frequency to it, but the drive is not able to produce a nice smooth sine wave. They haven't come up with a drive that can do that yet, but the motor actually will run. It will actually change speeds when you change the speed here, when you change the frequency. So this is what the actual motor is actually seeing. If you see where my probes are down here, the motor is actually seeing these square waves at 60 hertz and 230-something volts. Now I'm going to hit the stop button. You'll immediately see the voltage start going down and the frequency go down, and the waves will start to stretch like a spring being pulled. So watch closely. I'm going to hit stop. 1, 2, 3, stop. And you see the waves actually stretching real slow. That's your deceleration. And then the voltage and the frequency is going down. Your frequency is now 40-something hertz. And see, the square waves are stretching. The frequency is getting lower. The voltage is getting lower. So a characteristic about all VFDs is whatever the frequency is, the voltage will be proportionally changing. So just an example. Now you're down at 0 right now. Okay. Now I'm gonna actually set the drive for half of the original speed. So if I go to the speed pot outside, and we're gonna set it to 30 hertz. My leads are moving around. They're just kind of dancing around right now. So it's actually ramping up now from a dead still, and I'm gonna watch that frequency there, and I'm gonna set it to 30. So I'm going to fine tune it right here a little bit. I'm going to fine tune. Now, so look at here. At 30 hertz here, this is 30 hertz. I can bring the camera in some. Hold on. If I had a cameraman, I'd have it made. excuse the camera here, guys. I'm getting it set here. But I tell you what, for a $30 Walmart camera, it ain't bad. And that one I got coming in, man, it's going to be way better. So for the summer class, you should be good right there. It's going to be better. So at 30 hertz, I've actually got the speed pot on the panel set to half speed. At 30 hertz, the motor's actually seeing 166 volts. Phase to phase, okay, AC not phase at 30 hertz. But phase to phase. So that is proportionally, approximately, it's not exactly half of 60, but it's, but it's way less. It's way less than 208 that's actually coming into the drive. So I hit stop. So right here, guys, don't ever forget this. If you're running something other than 60 hertz, your output voltage is not going to be what's coming into the drive. It's going to be something less, okay? So don't think that because the output voltage is some weird number that something's wrong. You've got to look at the frequency you're running at, and it's going to be roughly proportional, not exactly, but somewhere roughly proportional to the change you did in frequency. Keep that in mind, because I'm showing you this so that you will know what to look for, what to expect, leaving a VFD, okay? It's important. If I go back up and measure what's coming into the drive right now, I'm going to move this. I'm going to go back into what feeds into the drive on your L1 and L3 there. Look how you see that you had the 210 coming in, nice clean sine wave at 60 hertz. That's what you get from Duke Energy. All power plants, their generators are running, they produce sine waves at a rate of 60 cycles per second. So all the power plants in the United States run at 60 cycles per second. So one cycle starts here and ends right there. So a whole cycle is here, positive, negative, and stop at 0. So right in there is one cycle. You get 60 of them things in a second. Coming into everybody's building. That's what you get. That's what's actually coming into the drive right now that I'm probing. Go back over. What I'm probing right now is actually on the drive, what's feeding in. Now, I think that's going to be enough of this video. I want to show you one at 480 volt. Let me scroll forward. Looking, but that's the way all of them look pretty much. Okay, if I go back up to 60 hertz, but you see how how jagged those edges look on the waves, how jagged that looks. We're going to go back. You see how uneven that looks at the tops of them?
Yeah.
Now, listen, this is artificial. This is actually constructed from DC inside the drive, and there's a computer in there in these VFDs that actually generates those pulses. So what you're looking at is the whole reason why you got to have a specially insulated motor that can handle that, because all of that, these jagged edges in there creates. It actually, if you read in your book, it says it creates vibrations inside there where the windings are in the motor, physical vibrations in there that can actually cause a cutting of the insulation and a breakdown and a shorting out of the motor. So it will cause a motor failure on just an average insulated motor that cannot handle this. So back up to 60. And another thing is some of your multimeters are not going to accurately read this. The only standard handheld multimeter that's going to read this accurately is one that's called True RMS. You see that RMS up there? If it's a True RMS meter, a scope or a multimeter that's True RMS, it can read a square wave accurately. It can read signals that are not 60 hertz. So when you get away from 60 hertz and then you don't have a sine wave, like this is a square wave, anything that's not a sine wave is called non-sinusoidal. Sinusoidal means that it has a characteristic of a nice smooth sine wave. This is non-sinusoidal. Sawtooth waves are non-sinusoidal. So a cheap multimeter, cheaper multimeters cannot read anything but sine waves accurately. You get away from sine wave, and you're going to get a bogus number on a cheaper meter. So keep that term RMS. Remember that, and that's a key factor when you're testing signals that are not sine waves, and that they're away from 60 hertz. So I think we're done with this. You should have one in your plant. It's actually getting a higher reading, and somehow the scope is actually calculating a higher reading than this meter is. And the scope has to be a little more accurate than this is. Let's just do a comparison there. So it's showing that at 60 hertz. Now let's see what happens if I check incoming voltage. The incoming voltage to the drive is actually is 210. That's what's coming into the drive right now, 210 coming in. Now let's see, does the scope say the same thing or what actually comes in? Because that's got me a question in my mind is why is it reading a little higher on the output
to a multimeter?
Why is the scope getting a higher reading on the output?
And they'll
So
match
we're going
on
to compare the scope on the
the
incoming side,
you know, because the incoming is a standard sine wave. So
and we've got our so that's coming in right there. And the scope's actually showing 210 coming in. So when you're reading a pure sine wave, the scope and the meter will agree. But when you're reading something other than a sine wave, the meter's not going to be quite as accurate as that scope. So again, the scope is going to be more accurate. They match each other when you're reading a sine wave, the scope and the meter do. But when you're checking what leaves the drive at the bottom of it, what's leaving that drive, then the scope is going to be the most accurate thing. But a lot of people don't have a scope, but a maintenance group really should have one. You should have one in your plant. It's worth having. Now let me fast forward. I'm going to hit the start button. This is a basic meter that shows you, and then you see the numbers go up. So as the frequency goes up on the drive, you see the voltage going up. So just keep that in mind whenever you're diagnosing VFD signals, what's leaving them. Your voltage leaving is going to be proportional to what's coming in. You know. So there's, you know, if the cheaper meter's what you got. I've had someone ask me before, you know, that there was a disagreement between two guys in the plant. One guy said the output voltage is always supposed to be the same, but it's not going to be. It's going to change proportionally with frequency. Okay, so there you have it. You can use these, but they're not going to be quite as accurate as a scope is. That's not true RMS. The scope is, and and I'm just trying to on this last day to try. Now let me switch over to a 480 volt video I did today, and then we'll wrap it up. So let's see, where are we at? I did one of a 10 horse drive. Let's see, that's not it. And let's see, right there. Now that was the PowerFlex 4. Let's go back. Right here. And this is a short video. This is not long at all, guys. So if you've never seen the signals of a hello. Okay. Now this is our third and final video for today I'm making here at the college for ELC 117. This is our last day for ELC 117 for this semester. And I wish we had more days, and I wish you guys could have been here. But anyway, one last video here that is very vital that you need to watch closely, unless you've already got field experience working with higher voltages. This VFD we're going to look at now, it's the one in the center of the shop. It's one that Butterball donated, and it's a PowerFlex 70 drive. It's bigger. It's for a 10 horsepower motor, and it's a 10 horse drive. And it runs on 480 volt. Now I'm going to move the camera. I'm just going to show you the drive and show you the motor itself that is running. Okay, so there goes the drive itself. It's a PowerFlex 70. It's bigger, of course. It can handle a 10-horse motor, and this is a big 10-horse motor that's running right there. So Butterball donated the motor and the drive. And what I've got here is I have simulated a Butterball setup that they have at their plant that they wanted me to teach. So the first thing you're seeing right here is this is a motor control bucket, what they call a bucket. It slides into a wall structure with a lot of units like this. And each one of these buckets they call controls, it feeds power to one motor or to a drive. So this disconnect and the breaker inside, there's a circuit breaker inside, and there's also a motor starter. So the motor starter, if I open it up, there goes the motor starter. It's a big, it's a NEMA.
That's a NEMA 2.
It's a NEMA 2. So you see NEMA 2 in there? So it's a big one. Let me set the camera down. I've had a cover just popped off this thing. So anyway, I'm going to make this short and sweet here. I want you to see what the voltage is
short, so just
coming into the bucket here. So the power coming in, it goes into a large circuit breaker in here, comes over in here to a manual starter, and then the manual starter leaves out of the bottom of it, and it feeds over to the drive. So this bucket here would actually be maybe on the second floor, above production where it can't get wet, and also that drive would be up there with it. But this is the disconnect here for the drive. So we're going to look at what is the voltage, the 480 volt. I want you to see what 480 volt looks like and how different the readings are going to be from what you've been doing. So get the camera over here.
This only goes for just a couple of minutes.
And let me get it mounted to the stand.
I know everybody's getting tired. It's worth
looking
at.
The turbulence here with the camera.
Is
I
that
would love to have
video
a camera person to help me, but I don't. What now?
Is that video real choppy to you? Or does it look smooth on your computer?
No, it's choppy. It's choppy.
Okay.
I'm moving around a lot. When it gets still, it clears up. If you look, it'll clear up in a minute. So, it is what it is. So,
Okay.
It's a little bit bumpy here, but hey, we're all right.
It's mainly me moving around the way I'm doing.
So this is where the power comes in, the 480 volts comes in. And I want you to see.
I'm comparing
what the voltage is.
480 volt coming in and then what's leaving the drive.
Right there. And let me get my gloves on.
So that's the disconnect for
this
the
is
drive.
480 volt. This is definitely some high voltage stuff here.
Watch the meter close. And we're going to look
just a general rule of thumb, guys, is this. Whenever you read phase to phase on three-phase, you got three-phase power coming in there. If it's 480, in general, what you're going to get is somewhere in the neighborhood of 480 volt leg to leg. Let me get myself out of there.
I'm all the time fighting, trying to stay to keep a clear view of something.
Let's see if I can get in there and then get out of the way.
Shadows. It's always a challenge when you're doing all this by yourself. There you go.
Now, so I'm reading from leg to leg there, and I'm getting 487 or 488, okay? So you're seeing that right there. It's 488 leg to leg. The nominal voltage would be 480 from phase to phase. So whether I'm reading from L1, now I'm reading the L1, hold on, get the camera over here.
And then my hands are kind
of. I'm reading L1 to L3. And now I'm going to read L2 to L3. That's also 487. And then I'll read L1 to L2. 490. So somewhere in the ballpark of 480. Now, reading from phase to ground is something important I want you to see. If you go from each phase to ground, you're going to get roughly 277. You're getting 280 volts from each leg to ground. So I'm reading from the first leg in the panel right there, if you can see that. I'm reading for L1 to ground, feeding into the bucket here. And I'm getting roughly 270.
Now, I stopped it.
You might be wondering, well, why, when you measure phase to ground with 480, why are you not getting half of 480? Why are you not getting 240? It has to do with, it's got something to do with a number called the square root of 3. If you take a number that's 277 and you multiply it by the square root of 3, which is 1.7, just say, let me do it on a calculator here. If you multiply 277 times the square root of 3, it gives you 480. Now, I can't explain how they came up with that, but that's the mathematical reason that it's 277 leg to ground. Again, I'm not a mathematician, but I just know that is the reason. So if you multiply, just see, if you take your calculator, and if you go to let's see, square root and hit 3 and hit equal. If you hit square root and 3 and equal, and let me bring it back in where you can see my phone here. You see that number there? 1.732. If you take 277 times 1.732, that's the square root of 3. It will equal 480. And that's all I can tell you. Beyond that, I can't tell you because I'm not a mathematician. But let it roll on. Watch. Just remember, 277 is the number that will be nominal. That's L1 to ground is 280. L2 to ground is 283. And then L3 to ground is 282. So just remember, phase to phase, if it's a 480 system, phase to phase, roughly 480, but it can be higher. At the plant I worked in, sometimes it could be as high as 490. Now, right now, it's 490 in here. I've actually seen it 495 where I used to work at. But roughly 480 leg to leg, and then leg to ground, remember, 277. Now, if you ever hear anybody talk about lights, like lighting in plant lighting that's 277 lights, what that is they're taking one hot leg out of a 480 panel like this, and then they're using neutral, which would be 0, and they're getting roughly 277 to 280 right there. And they would use one hot leg out of a 480 panel and a neutral and a ground, and it would give you that 277 or 280 right there. It would actually run lights like, I'm just going to bring it up to show you one of the bay lights in here. So that bay light right there, if you're working around somewhere in a plant that says, do you know anything about 277 lights? Well, here's what you can say. That 277 light runs off of one leg out of a 480 panel, one hot leg, one neutral that's 0 volts, and it runs on a ground. So it has one hot, one neutral, and a ground, and that's what fixtures like that run on if they're 277. So the panel,
I learned something today.
The breaker panel that feeds this is called a 277/480 panel because each leg is 277 to ground, and then phase to phase it's 480. Okay, now let's move the camera and let's come over to the motor. When you go in a breaker panel, if you go in a panel that's got 480 in it, and in the breakers, look up at the top where the nameplate is in that panel, and it's going to say 277/480.
Okay.
Now, if you go into, because each leg is 277 to ground, now that panel is going to have three phases in there, L1, 2, and 3. It'll also have a neutral, and it'll also have a ground. There'll be 5 wires in that panel. Now, if you're going to motors, it's just going to use the 3 hots.
Mm-hmm.
Okay, if it's a 3-phase motor. Okay, if you're doing lighting, it's just going to get one leg. It'll be a single breaker in there, a single pole breaker with one leg, and it will also grab that neutral because it'll take one hot leg, a 277 leg to the light, a neutral coming from the light for a return current to the breaker panel, and then the ground is used actually just for the metal parts on the fixture for grounding. So that's what you commonly see on lights if they're high voltage. It'll be a 277, and that's the meaning of that. Okay, so other panels you go into, if you go into a 240 panel, you look up at the top, it's going to say 120/240 because those are the two voltages. Those phases are going to be 120 to ground, but phase to phase 240. Now, at the school, we've got a panel that says 120/208 because they didn't bring 240 into the plant for some reason. And I need to ask somebody with the power company, why in the world don't you just give everybody the same thing? I don't know the reason for that. Why in the world we got 208, not 240? I don't know. But the panel, when you look in the panel, it says it right up at the top. It says 120/208 in one panel, and then the other panel says 277/480. So the first number is phase to ground, and the second number is phase to phase, and that's the meaning behind that. So
we got a bunch of them like that.
That's confusing.
It's confusing. Is that Justin?
No, that's Pat.
Pat, confusing. Okay.
Yeah, the 208 and then the 230. You know.
Well, okay. Now a motor. A three-phase motor, if it can run low and high voltage, this motor here in the back of my truck, seriously, if I take the camera, let me go to the motor. You see
now, I can understand the motors will run off of it. What's confusing is how they get those different currents.
Those different voltages.
The different voltages, yeah.
Now, the voltages, what's determining the voltages is this. Okay, when you go outside in the yard and you look at the top of them poles and you see them big old transformer cans up there.
Yeah.
Those metal cans.
Mm-hmm.
Okay, going into the transformer up on the line, it may be it may be 13,200 volts. There's no telling. There's all kind of different voltages that you can have on power distribution systems depending on what neighborhood you're in.
Right.
But whatever it is feeding into that transformer, the transformer does have a definite step-down ratio, okay? And so for whatever reason, the step-down ratio, it varies depending on where you are and what transformer they put up there. And so it's a step-down ratio of what's out there on that light pole. And what they step down to, that's what you're going to get. Unless on your property, then you change it through another transformer that's maybe sitting out in a pad outside the plant.
Right.
And so on the college campus, there are large transformer pads out there on campus that are doing just that. So, but I honestly don't know why in the world that they chose in some places 208 like at our school.
Mm-hmm.
I've always meant to ask somebody, but I never remember to ask them. So at my house here, our stove and our dryer and all is running on 240, but guess what? It ain't 240. It's about 250.
Mm-hmm.
I'm serious. It's hot, man. I mean, it's, but a low voltage motor that's rated at say 230 like this in here at the back of the truck, that motor would run at 208. It would still run at 208. And I think it would run fine at 240 or 250. Probably would. 230 is nothing but it's a middle of the road number. It's kind of a midpoint in the low range in the 200 volt class. It's a middle of the road number, and on the high side, this motor says 460, but guess what? Bring the camera over and it says, 460 over on the right side, but that motor would also run at 480 too. And my guess is it will probably run as low as 440. So 460 is a middle of the road number between 440 and 480.
Mm-hmm.
Some plants actually have 440, and chances are that motor will probably still run fine at 440 or as high as 480.
Mm-hmm.
It's just the 230, 460, they're middle of the road numbers. So the average motor that I've seen, can handle a tolerance in there like that, so anyway. Now, let me fast forward it to you, that you see the oscilloscope on this high voltage here, and then that'll be enough, and I won't hold you guys anymore. I'm just going to fast forward it some. Okay, there's that motor there. Now I'm gonna let's see. Let me get my stuff together here. I'll skip beyond that and just show you the scope itself. Two numbers there, 3-volt motor running, and I'm just going to go from phase to phase on it and see what we get. So this is the 480-volt motor. Now watch it. We're on auto, and I'm going from phase to phase right there. You see the square waves there?
Mm-hmm.
But look, and the reading says 0.526 kilovolts. But let me move it in. It's actually auto range into a kilovolt range because that meter, if you notice right now, the scope is actually reading in millivolts. Now you're going to see that change that's in front of the V to kilovolts whenever I hit this this higher voltage. So I'm going leg to ground right now. You're getting a square wave, if you notice that, like the book shows you for VFD outputs. Square wave at 60 hertz and actually 526 volts. You see it? So it's at 526 volts. And my probe just moved here. My hands are not steady on this stuff. They keep moving around. I'm sorry, my probe is moving around. Now, I got it stabilized. It's actually saying 0.526 kilovolts now. It's moved again. So that's the equivalent of 526 volts when you're in kilovolts. I'm going to hit the stop button. You're going to see it actually slow. Do y'all see that K in there?
Yeah.
Yeah.
So it's a very smart meter. And what it tries to do is it tries to, when the signal, when the waveform gets so tall, it starts approaching the top end, it'll actually change the volt, which is changing how many volts it is per square on the grids in here on the scope. You see those square grids in there?
Mm-hmm.
So each volt, if you look down in here, it says right here, you see 500 V per D, that's 500 volts per division. Do you see my mouse moving around?
Yeah.
Now, so the volts per division means this. For every square grid on the scope screen, how many volts it is equals one square grid, like on graph paper. That's like graph paper there. Well, 500 volts per D per division. So you see that? Mm-hmm. Now, when it auto ranges into kilovolts, then everything looks smaller, but then the volts per division changes. It goes to a higher number. If I back it up, let me back it up, and you'll see where it was. That was actually different. Volts. Now it's moved again. Let's back up. So that's the equivalent. You see it? So it's at 500 right there. Now, bam. Now look, I called it. Look here. I called it red-handed. Look, that says 526 volts up here, not kilovolts. RMS, 60 hertz. But look, your volts per division. What does it say now?
200.
200 V per D. So each grid is 200. You know, you got 200. And you got to see wherever the midpoint is in there. This actually looks. It's
200 per line.
200 per line. So so it's just under. It's not 600 volts, but it's over 500. But the grids are now used to when I was using the oscilloscope back in the 80s, when they were not handheld, you didn't have this up in here. You didn't have none of that. You had to actually count the grids and look at your selection switch on the scope, and you had to do all that calculating in your head on everything that we did back in the 80s out there at Sampson Community College. But my degree is in electronics engineering from the same college you're going to now. But it was from 84 to 86. I was out there 2 years. And I used these very, very large scopes that looked like a television screen. I mean, it really was a picture tube. And I could show you sometime at the school where the scope that I used 30-something years ago is still out there. And I can still show you that it works. So we kept that. Okay, let it roll. 26 volts. And my probe just moved here. But you watch that volts per division change down there. I'm sorry, my probe is moving around. To see it change. Now, I got it stabilized. It's actually saying 0.526 kilovolts now. It's moved again. But, when it changes the volt per division, the physical signs of the wave looks like it's smaller, but don't let that fool you. The voltage has not decreased any. It has only changed the volts per division. And so you're seeing that, and you look at your metric prefix, your kilovolt or kilovolt. So that's the equivalent of 526 volts when you're in kilovolts. I'm going to hit the stop button. You're going to see it actually slow down in frequency in the small screen, and then the voltage will also decrease. Watch it actually. So now you see the waves actually stretching out. Well, actually, it just stopped because this doesn't do this drive is not set up to do deacceleration. It's just set up to do. It's just set up to do acceleration on the beginning. Butterball told me that instead of doing deacceleration on this drive, they wanted to cut it off and let it coast to stop. They wanted the pump for this drive to actually, when they hit the stop button, they want that pump to freewheel and stop on its own. They found out that on the brine pumps that are shooting brine into the turkey through the needles in their needle injection, they found out that if they ramp the pump down, the inertia of the pump actually causes some feedback, regenerative feedback, and it causes the drive to fall out if you deaccelerate the pump.
Yeah.
They cut the deacceleration off and let it just coast to stop. They do ramp it on startup, but they just let it coast to stop, and they got rid of that bug. So Eric out there has found out all kind of little things by kind of playing around the drive, what's particular for their applications, you know. So you said yeah, Patrick. So does that sound familiar to you?
Yeah, we've had issues like that before.
Right. So a motor, if a motor's got a lot of inertia to it, and when you cut it off and it wants to keep going because of the load the weight of the load that's kind of making it keep going, when you cut that drive off, what's going to happen is that motor turns into a generator.
Mm-hmm.
And that motor, when it turns into a generator, it has regenerative feedback going backwards into the drive, and the drive don't like that. It'll fall. It'll have a regen fault, a regenerative feedback fault. It'll shut off. So they've actually got drives out now called regen drives that they use at Schindler. Schindler uses regenerative drives on escalators because if you have an escalator and you got a lot of people on it and it's going downhill, for instance, and you stop it, the weight of all the people on that thing forces the escalator, it has inertia to it. So the motor ends up freewheeling and going forward, turns into a generator, shoots it back to the drive. And what these drives do is they actually funnel that regenerative energy back onto the power grid. It's called a regen drive, a regenerative drive. And you can look them up, Google them. I mean, they're popular on anything like elevators. Elevators have to have them. Escalators have to have them. Anything that's got a lot of weight to it, that once you shut it off, that the load itself just kind of carries that motor on for a while. But they got these smart drives that take that regenerative energy, funnels it back through the circuitry, shoots it back on the power grid in sync with the 60 hertz coming in. And the grid actually can reuse that. It's wild, man. It really is. But that's what they're using on some things at Schindler. Okay. That's what the supervisors told me about those drives, and I looked it up, and it's exactly what he said. But watch one more time. So let's start it up again here. You'll see it start up. We're going to start it up again. I'm hitting one more time here. Hold on. Stop. That's my phone. Somebody's trying. My mother's car broke down today, she was calling me. And in the morning I've got to deal with her. We're going to start it again. Here we go. So watch it close here. So I'm starting to drive up again, and you're down at 20-something hertz, and the voltage is going up. You see that the frequency is increasing. You see it shrinking in there. And then you're going on up. So the voltage eventually came up to 526. And my hands keep moving around. My hands are not stable when I'm turning around here. Let me get my hands stabilized, guys. Sorry about that. So you're sitting there at 0.526 kilovolts, which is 526 volts. And you have the square wave there, and you're at 60 hertz. So anyhow, you see those ragged edges up there on that wave?
Mm-hmm. Yeah.
Now, you see all those spikes in there, how nasty that looks, how ragged that looks. Now, that's actually the best that drive can do. That drive can't do any better than that. But those spikes is the reason why the book says that your motors have to have extra insulation around the windings because those spikes can actually cause problems, a breakdown of insulation, and actually a movement, a vibration and a movement in there. Let me find where it said that, because I never really knew about the movement of the windings. I knew that the spikes could actually cause a breakdown of insulation, but I didn't know that that they would actually move. Let's see. Differ from that. Let's see. Now, if you look on page 348, this is no joke, man. It's in your book. I'm gonna read it straight. I'm gonna read it straight to you. Matter of fact, I'm gonna shoot it on the screen up here. If I can find it, let me cut screen share off right here. This is plumb wild here to read this. Okay, you see that?
Yeah.
Inverter rated motors generally have insulating paper between the windings and the stator core. High voltage spikes produce high currents that produce strong magnetic field. This increased magnetic field causes the motor windings to move, actually move. Like a magnetic fields repel each other, the movement can eventually cause insulation wear off of the wire and produce a grounded motor winding. Isn't that wild, man? I mean, that I had never heard that. I knew that the spikes could damage the insulation, but I did not know that the repelling fields in there would make those windings physically move and just wear, you know. So anyhow, this book is, you see in our book, you see what it is showing here, the image there. So it's exactly what you see with the scope. So so this is pretty good information if you're kind of like me. I'm into I want to know why. You know, I want to know why. Why this or why that? You know, I like a kid. You know, you know how youngins always saying, well, why? You know. So anyhow, so that's pretty much it. And if I change this, say, to 30 hertz, you're going to see it be proportional, like you did on the other one. I won't take time to do all of that. Well, actually, I will. I'll take just a second to do it. You know me, I'm long-winded. I'm going to show you at 30 hertz, and then I'll hush. But I get into this kind of stuff. Not many people do, but if you get into it, it's really not complicated. And you can be one of the few guys I'm going to slow the drive down that can really analyze this stuff. And we're going to find out roughly. I mean, what is the voltage on this one? Roughly around 30 hertz on the 480 drive. I was wondering where I worked at. I wanted to know more about it. All right, so now the motor's at 30 hertz here. I'm going to put the probes back on there, and you should see 30 hertz showing up on the bottom screen, and it does. You see that? It says 30 hertz on the screen and 0.374 kilovolts, which would be 375 volts. So always keep in mind, guys, that if you're running at something other than 60 hertz, your voltage is also going to come down proportionally. That's the way the VFDs are designed. And we're going to get into why that is, but they have to do it that way in order for the motor to perform right, for it not to overheat. When you slow it down, you also have to decrease the voltage from within the drive. And that goes back to when you decrease the frequency, the inductive reactance, which is a magnetized sort of a resistance that develops when the motor runs with power on. Inductive reactance is ohms. It's actually ohms, but you can't read it with a regular ohm meter. It's only there when it runs with power on it. And when you decrease the frequency, the inductive reactance, the ohms of that goes down, which makes the motor current rise. So if you drop the frequency and you don't drop the voltage, the amps would become so high that the motor would overheat and it would actually damage the motor. So the designers of the VFDs, when they saw that way years ago, they combated that by having a proportional voltage change when you decrease the frequency, and that solved it. That solved the problem. And so that's the whole reason. I'm one that wants to know why. You know, so I like to know kind of a subject inside and out. I like to be able to do that. And when you inquire that way, you find out that a lot of things are simple. That don't seem simple, that they become simple when you ask these questions. Okay, so that's going to be it. I'm going to shut this thing off. You guys have hung with me. You guys are the champions, man. You guys are the special forces of ELC 117. Because I've got to get ready here for ELC 215. I'm teaching this afternoon at 2 o'clock in just a few minutes. So thank you for watching. And you can contact me at any time if you have questions on your job. I'll help you beyond this class. So this is not just the end of it. So you got my number. You can text anytime, and I can help you day to night, whatever, with any questions you have. And if I don't have the answer, I think I can find the answer. I know a lot of people that know more than I do, and I know right good bit, but I know some pretty people in some high places. So thanks again for joining me, and God bless you. Thank you, and thanks for taking the class. And if you're not finished with your degree, continue with it until you finish it, and it'll be worth it. It'll be you'll be glad you did. So thanks for joining me.
I'm trying.
Yeah, and if you let's see, go back. I'm gonna do a stop share. Would you guys, if you just take your time and don't look at how long it's gonna take. Don't you even think nothing about that. Don't look at how long it's just gonna take. The main thing is if you take one class at a time or two, take whatever you can do and make an A at it. Make an A. Make all A's.
That's what I've been trying to do.
And your transcript is going to be there permanently. I'm just going to tell you a story. This is a true story that it surprised me. Now, I graduated from our college in '86 with an electronics degree. I graduated with 3.7 out of 4.0. And so I got out in '86. I started working in the industry. I worked in the industry to 2009. And then the plant shut down. I went to a control company and worked part-time for a while. And then the school needed somebody, and a friend of mine worked there, and he said, "Hey, man, you know, Continuum is looking at electronics instructor for Butterball." And I said, "Really?" And he said, "Yes." I went out there, and guess what happened on the interview? Katie Brown interviewed me, and she said, "I need your transcript." And I said, "Well, Katie," I said, "it's right here at the school. Can't you just kind of pull it up on the computer?" She said, "Oh, no, they won't let me see that." She said, "They won't let me see that." She said, "You got to go over there to the registrar and get one that's sealed up that ain't even been opened. And you got to give me a unbroken sealed transcript for me to look at. And that's going to set you starting pay." And I said, wow.
Oh yeah.
So I went over to the registrar, student services, and I said, "I need to get a transcript from 1986. And they pulled it right up, bam, they printed it, sealed it in an envelope. I took it back to Katie Brown. And man, listen, let me just tell you, man, I was happy that day. I was happy. She looked at that transcript, and she looked at me, and them eyelids went to blinking. She got a blinking, and then she'll turn that head, she blinking like that. And she got in her computer and looked up a pay scale based on a number of years experience and grades. Grades. She looked at the entire transcript, all the grades, and then the final GPA, and she punched some numbers in, and she says, "I can pay you this amount." And I said, "Okay." Because, hey, I never made that much in a plant. Now, where I worked at was not really top pay in Clinton. Smithfield Packing paid more than we were paying. But at the time where I was at, it was average pay. And but at the college, I mean, they started me out making, $4 more an hour than I ever made in the plant.
Okay.
Seriously. And I thought to myself, you know what I realized right then? What I already knew. I said, all of them nights I studied on the average of at least 2 hours, an average of 2 or 3 hours a night, every single night on electronics, because a lot of math involved in it. A lot of calculations. It was very, very. It was an engineering class. It was electronics engineering. There was no mechanical anything in it whatsoever. 2 solid years of nothing but electronics classes. It started out basic electricity, analog electronics, digital electronics, microprocessors, robotics, biomedical electronics, receivers and transmitters. A lot. You could have really had a lot of choices to go, routes you could have went in. And I realized that day when she told me what she'd start me paying, is I said, thank God. I said, I am glad that I got into it that much to put that many hours in it. I just kind of got engrossed in it, you know. Mm-hmm. And I had a study partner that was ex-military. He was in the Air Force, Willard Brockington. And me and him looked like totally opposites. I mean, you'd look at him and look at me, and you'd think they wouldn't never be like pairing up. But man, we paired up, and we were special forces in that class, I'm telling you. On the weekends, we would take turns. I would drive Slim to Fayetteville, on the other side of Fayetteville, where he lived at Holly Springs or somewhere over there. And we would study. We would battle it out. This guy was so good on analog because he was ex-Air Force on analog controls. I struggled with analog. He struggled with digital. Digital was so easy for me. Logic gates, you know, and, or, nor, and all these different logic gates that was in there. He had trouble with it. So I helped Willard on digital. He helped me on analog. And I'm telling you, man, we come out of that thing on top. Good. I had the president's list 1 time and the dean's list 3 times in 2 years. And so your transcript will go with you 30, 40 years down the road, and it can determine your pay rate way down the road. Mm. And so some of these young guys, man, that are not, they're honestly, man, their eyes are not, they're so hazed and they can't see clear that they're squandering the opportunity by not trying to learn everything they can here right now. I mean, I know what these guys are heading into. I know what's going on in the plants. And if you learn everything that I'm trying to show you, it gives you a good start. It's not everything, but it's a very, very good start. Right. And they're not even getting that because they're not coming to the table to eat, man. I relate to a restaurant. Right. If I had a buffet and I worked the hardest I could to make a good buffet and 2 or 3 people come and they fill up, I feel good about that. But what about the other people? What about the other ones? Are they not hungry, you know? Evidently not. Or they come in 15 minutes and bug out, you know? So yeah, I guess it's like when you pay $13 to go to Salem Pizza in Salemburg and eat on that nice buffet. If you eat a little saucer full and leave, I reckon that's all right. But you could really fill up, you know. So, but I just relate to restaurants. I just feel like I'm serving a buffet kind of, and I'm trying to make it as good as I can for you guys. Yeah. And I call it the educational buffet. It's what I call it, you know.
Yeah, you gotta eat it.
Barney, he said, "My God, educational buffet." I said, "Yeah." You want your fish, your chicken, you know, you want your salad, you know, you want your string beans, your taters, your slaw. You want to have a wide variety here, Jamie. I'm talking about.
I know exactly what you mean.
You know what I'm talking about.
My problem with buffets, though, my stomach ain't big enough because I don't eat a whole lot at one time. I want to eat, but my stomach ain't big enough. But I'll be full when I leave now. Right.
Yeah. Okay. I got you. Yeah. Well, I quit going to buffets because I've had double knee replacements, but yeah. and I've had to. I'm eating a lot of salads. I had a salad today with like chicken nuggets on it. If I'm Arby's, you get a farmhouse salad with crispy chicken. It's got like bunch of popcorn chicken on there, real good on that salad. It's really good. It'll fill you up, man. And
that's cheating though. That ain't salad.
It ain't. It's keto though. It's meat and salad. I got to have some meat on it, Patrick.
That's a salad with your meat.
Right. I'll go over there and I'll tell them to put roast beef on the salad in the place of the chicken. And they'll put slices of roast beef on that salad, and I'll have a roast beef salad, man. I love that. It's good. So
good.
I eat that a lot of days. That's exactly what I eat. But I'll switch it to the crispy chicken and eat that sometimes. And they got pretty good turkey on there, too, so you can flip it over to turkey. But those salads is the main thing that's helped me go from 295 down to 260.
Wow, okay.
I've lost that much eating them salads with meats on them.
That's good.
Good. Low carb, low bread. So it's the carbs that really works for me. If I can still eat meat, I'm okay. I can survive. It doesn't mess me up in my head. It doesn't make me feel like I'm, depriving myself. So
yeah.
So it's helping me a lot. But
all right.
Anyway, but thanks, guys. And I'm going to stop the recording, and I'll post them. I'll try to get both of them posted before I go to bed. And if YouTube will take them like that. So so anyhow, but Tuesday you can look for the exam on there. And what I'll do is I'll log on. I'll set up a session at 6 again for folks that want to take the exam during the normal time. If you want to take it earlier, that's fine. I'll open it up to say from 9 o'clock in the morning to say 9 at night. And that way, if somebody'd rather take it in the morning, they can. Afternoon, whenever you want to take it, I'll have a wide range. If Moodle will let me set it up that wide, and I think maybe it will. I've never tried nothing that wide, but some people kind of would rather do it earlier.
Yeah.
And
some of us got to work.
Right. So just keep this in mind. Whatever time you try to log on and take it, if you have any problems with it, if something's not right, something's not going right, then just call me. Call me on my cell phone, and I'll help you figure out what's going on. But you shouldn't have any trouble with it.
Okay.
And it'll work out. It'll look like a worksheet, but it's just going to be basically it is going to be a worksheet. It's going to be I'm going to take your worksheets. I'm just going to pick a couple of things from chapter 7 through 12. And I didn't give a worksheet for 37. For 36. Okay. I gave one I didn't give one for 37 either, because I figured there wasn't time to get them for people to even do them. So I stopped at 12 as far as worksheets. And so it'll consist of chapter 7 through 12. And it'll be a few questions out of each one. And I'm going to put a reference in there with each question as to what chapter it comes from. You can just let it be open book. You can do that. You can go back and look at your worksheets. You can print your worksheets from Moodle. And if you're going to print them and save them, you need to do it now before they actually shut off this Moodle section.
Yep.
Because when they shut it off, you're not going to be able to get to it. It's going to be it. And I'll do a backup when I turn grades in. I actually do a backup every time I do grades. And when I do a backup, it actually saves all of your stuff. It saves my grade sheets. It saves the templates of the worksheets and all. It saves everything in this big, huge backup. And I do that every time I grade. So, but if you simply save your worksheet to your computer, it's going to be a Moodle file. I don't think you're going to be able to read it later and not be in Moodle. So I'd print a paper copy if you want to save your worksheets. I would myself, and then you got the physical copies to keep from on down the road that way. I've kept all my stuff from years ago, so just do that. And again, I'll log on about 6, and I'll kind of hang out, and I'll text everybody. I'll say, if you need me during the exam, then I'm here. Then let me know if you got issues going on, and I'll help you through the normal time period. So, and then after that, I'll start grading them on that Wednesday. And as soon as I get everything done, I'll put the finals in Web Advisor. And if you check Web Advisor, then you would see your final whenever it posts. And grades are due the following Monday. So, but I'll have them done before the end of the week. I know I will, because we're going to be done on Tuesday. So by Friday, I'll have, and maybe by Thursday, I may have it all done. So, and then there's a gap in there. I've got a lot of getting ready for the PLC class, because it's going to be online. And I've got permission from Rockwell for everybody to download RS Logic 500 and an emulator program that'll actually run the logic like a PLC on your computer, and Studio 5000 with an emulator. And so people are going to learn how to write the logic. I'll give labs. I'll show you how to do it, and then you'll actually write your own programs. And you'll click screen share and flip it. Let me see your thing run in your emulator. So I'll actually see your logic run. If it does it, I can coach you, because everybody in the session can do screen share.
Mhm.
And so we're going to do some flipping of screens, and I got a lot of ideas to make it work online to be the best we can. Plus, I'm going to have a PLC sitting right in front of it with a camera showing the physical wiring. I'll actually go through the wiring physically, like what I've done with this thing, and show you the devices we're wiring and what the lights look like coming into the PLC, the voltage with the meter. So that whatever project that I'm asking somebody to write a program for, I'm going to show them the physical PLC. This is what it looks like if you actually had real push buttons coming in, a solenoid on the output or whatever. And I'll show the real physical machine, but we're going to run them on an emulator. And the emulator actually is a nice thing, because all you got to do is go in there and trigger one contact on the start button. You go in there and toggle a bit, what they call toggle. You can right click on that contact and toggle, and it's going to start your program. It's going to run, and in the emulator, you'll see the green. It'll be just like running on the PLC, you know. So I got to get 20. I got 20 people already signed up for this class. 20. So I've got to communicate with 20 people and make sure everybody gets all this software downloaded on their laptops, and that we can start rolling. We've only got 8 weeks to make all this happen with 20 people. So it's a lot going on, but I'm excited about it, because Rockwell, we've been blessed. The Lord's blessed us on this thing, man. I would have never dreamed it. I was looking at generic software to do this. Something told me call Rockwell, because I saw a guy on YouTube saying that you could actually download the emulator and all free.
Mhm.
I got it with Rockwell, and man, they said, well, since you're on the educational subscription list and you pay a fee every year for software, we're going to let you actually download the real stuff.
Okay.
The real stuff, man. Yeah, the 500 and the Studio 5000. So everybody, all 20 people will have the real McCoy stuff loaded on their computers.
Oh, that's good.
And it'll run for 90 days. It'll run for 90 days. After that point, it's going to stop, but it's still on the computer, but it's not going to be activated. But after that point, if their company would pay for reactivation, then they could just continue to run it on their computer if the company paid
But that's
for
expensive.
reactivation, you know. So
Expensive though.
it's very expensive, but let me just tell you, man, you can learn in the time frame that we've got.
Oh yeah.
And the way that I go about it, believe me, you're going to learn enough. You'll be surprised. You'll be surprised what you can learn in that few weeks.
Yeah.
You'll know enough that you can go in and modify programs on machines, write them from scratch. You'd be a good right arm man for an engineer, I'll say that. Where I worked at, engineer had me, it wasn't nothing strange for him at all to say, then listen, on this machine, we're going to add some cylinders on here, another function on this machine. And me and Alton's going to install it. We've already made the tooling and the brackets. We're going to put the stuff in, and you go ahead and get your PLC out ready, and here's what I want to do. And he'd tell me when he wanted the cylinders to go in and the clamp and all this stuff that we're adding to the machine. I'd go in there and I'd write logic and add into an existing program, and then they put the stuff in. I'd program. The engineer would watch it. He'd say, I want you to advance the time on this one and slow the time down on that one. He'd tell me how he wanted it. I'd go in there and tweak it with timers in the program until he was happy, and he said, that's what I want, Durwood. That's what I want right there. And so I worked hand in hand with a mechanical engineer that was he was really high advanced design engineer on mechanical things, and he depended on me for the controls. And so I've served in engineering functions. They didn't call me engineer, but I have done some of it. I've done quite a bit of it. So and I can pass that along to you. It's not really that hard to do.
And now you're a videographer.
I'm a videographer. That's right. I'm a YouTubeologist.
Yeah.
Yep. So
I took that class with Mr. Meredith. So, but it sounds like you guys are you're gonna get a lot more out of it doing it that way.
Right.
Yeah.
Yep. You'll learn a lot more on the software end of it.
Yeah.
And Patrick, if you decide you wanted to do it now, I would up the cap. We're capped out at 20 right now.
Well, the only problem with that is during the summertime. That's when we are wide open.
Yeah. So you better not then. Yeah.
Yeah, we are wide open. But I'll be in the ELC 215 though. So
that's January. That'll be here before you know it.
Mm-hmm.
Be here before you know it, man. And I'm as far as I know, Lord willing, I'm planning on getting that back surgery done like what you had done. I'm planning on getting it done in the middle of November.
Okay.
They give me permission again this year to shorten the semester by 3 weeks and increasing the hours, and for me to get done in the middle of November and get my back fixed. So
Okay.
it's them vertebrae are slipping, man. And I'm telling you, man, it's
put you down.
Yeah, it's this close to it right now. It's this close to it. It's sometimes when I stand up and sit down, it does a number on me that's different than anything I've ever felt before, and it's got me concerned, man. So I'm hoping and praying I can hang on until November to get it done, because I don't have to use as much sick time. You know, I build up 8 hours a month, and during Christmas you automatically get several weeks off paid anyway. You know. And plus, if I do it then, they don't have to find nobody to fill in for me, you know. And I like to cover my own bases, you know. I don't want a stranger coming in trying to fill in for me, and you don't know what you're getting. You know what I mean?
Right.
You don't know how well they're going to take care of your people. I just like covering my own bases. I like looking out for the people that are come my way, you know. So okay, guys. Well, you have a good evening, and I'm gonna shut this thing off and let it upload. And anyway, thank you. God bless you.
Don't forget to switch that thing off of private now.
Okay. Yeah, I made a note. Yeah, I'll change that. Thank you. If you hadn't told me, I wouldn't have known. So.
All right.
Well,
Thanks, guys. You guys have been awesome. You guys are the special forces of ELC 117, and I'm telling you, you're getting a badge right now. You're getting your stripes right here. You're getting them. You got a shoulder full of them right now, man. You are like Green Berets or special. I say special forces. So.
Well, I want my pen.
Right. Yeah, you got to have a want to, and you guys got to want to, and that's why I'm in it. Because if nobody did, I would just end up back in the plant. You know what I mean?
Yeah.
Which I could.
Well, thank you for all the stuff you've been doing, man. I know you've been going out of your way to try to make this happen so we can get through this.
Well, I feel obligated to, because you guys have come and paid, and I know where you're. I mean, I don't work in your plant, man, but I've been in that plant, and I know the environment you're in, and I know how seriously you need everything you can learn in this amount of time. And you made a good move getting in. Ronnie made a good move getting you in. I saw him that day at the grist mill, and he said, "Hey, I'm glad I seen you." He said, "I got a guy, Jamie Jones over there. He's a welder fabricator, and I want to get him in your class. Can you get him in?" And we already had 20 people, and I said, "Yeah." I looked over at Barney. I said, "Barney, can we get one more in?" He said, "I think so." So I knew as soon as Ronnie's a man that you don't say no to. You don't say no to him, because that dude he's a sincere guy, and he treats people right.
Yeah.
So when he starts something, then I try to jump on with him and help him. You know, he wanted to hire one of my graduates one time, and he couldn't find him. So he said, "Can you help me find him?" I said, "Yeah." I got back into the records at the school, and I found out the guy's address and all that, because we couldn't reach him by phone. So I gave Ronnie his address, and Ronnie said, "You reckon he'd mind if I went to his house?" I said, "No, he wouldn't mind. I know he'd love to have a job."
Yeah.
So Ronnie drove to his house down on Cartertown Road. He wasn't home, but he left a note on the door with a hog slat sign on it. And before Ronnie got home, man, Juan called him. He called him, man. And so stuff like that is, Ronnie's that type guy, man, to where when he gets on trail on something, it's worth jumping on with him. You know what I mean?
Oh yeah.
It's worth it. That dude, I mean, I like his style. I just like his style of doing things. So I try to drop what he called me. It was a Friday afternoon, man. I was getting ready to go eat some fish, and I said, "Wait a minute. Now Ronnie's called, man. That fish can wait."
It must be something you get that fish.
If you met this dude, you know what I'm talking about, man. He's the kind of guy that you just really don't want to say no, or you don't want to put him off, because
he's a good boss, man.
Whatever he's up to, it's everything I've seen him up to is worth doing. He recognizes the potential in people, and he gets his hand on somebody and wanting to do something, man. He knows what he's doing. He recognizes what's worth doing. You know,
he'll go out of his way to help you any way he can.
He will, and that's what I like about him, and that's why I helped him find Juan. And he's got Justin Williford out there. I recommended Justin. Well, actually, Justin was a forklift driver for him for a while. Justin wanted to break into maintenance. He come out to school and got his electrical certificate. And then Ronnie recognized him and got him in maintenance here at Five Bridge plant. So So that.
I know Justin.
Yeah, he's a good guy. I like Justin. Justin is very versatile, man. He's a real good mechanic, and he's a good electrical guy. You know, so he's
smart.
He's a right arm. He's a good right arm man to have around, man. He sure is. He's kind of guy you want in the group, man. So, but thank you. I'm going to stop talking, and you guys have a good night. And I'll see you Tuesday if you need me.
Okay.
I'll set up a session, and you can pop in if you want to. And I thank you.
All right.
Thank you. God bless you. Have a good night.
Good night, guys.
Good night.